What if everything you think you know about space and time is just the surface of something far stranger? We live inside a structure that scientists have been studying for over a century, yet it continues to resist our attempts to understand it completely. Space seems empty and still, while time flows steadily forward, but reality operates on principles that don't match these simple ideas. The very foundation that holds our universe together bends, stretches, and holds our universe together, bends, stretches, and behaves in ways that challenge every assumption we make about how things should work. Even the brightest minds in physics admit they don't truly grasp what space-time actually is, despite being able to measure and predict its behavior with incredible accuracy. In this video, we'll explore why this mysterious structure remains just beyond our complete understanding, and what that might tell us about the nature of reality itself. If you like these videos, I would appreciate if you clicked like or subscribed, as it's important for the channel and it helps others find it too, just like you did. Thank you. Now, let's get started. The most curious thing about space-time, really, is how it refuses to behave like anything we know. You walk through your house and space feels solid, permanent, like the walls will always be exactly where you left them. You check your clock and time marches forward, steady as breathing. But physicists tell us that this fabric beneath everything, this thing that holds reality together, actually bends and twists and changes depending on what's happening around it. Think about light for a moment. Light travels at the same speed, no matter who measures it, no matter how fast they're moving. This sounds simple, almost boring, but it breaks everything we thought we knew about how the universe works. If you're running toward a flashlight, common sense says the light should seem to move faster toward you, but it doesn't. The speed stays exactly the same. This stubborn fact forces space and time to become flexible. Instead, when scientists first realized this, it must have felt like discovering that water flows uphill. Two people watching the same events can disagree about when things happen, and both can be completely correct. Time itself stretches and compresses depending on how fast you're moving or how deep you are in a gravitational field. The faster you go, the slower your time appears to outside observers. The stronger the gravity around you, the more your clocks slow down compared to someone in weaker gravity. GPS satellites experience this every day. They orbit high above Earth where gravity is weaker, so their onboard clocks run slightly faster than identical clocks on the ground. Without accounting for this time difference, your navigation system would drift off course by miles within hours. So this strange behavior of space-time, this thing that seems abstract and theoretical, actually guides you to the grocery store. But understanding why space-time behaves this way, that's where things get murky. We can measure it, predict it, use it to build technology, but grasping it intuitively feels like trying to hold on to smoke. The problem is that our brains evolved to navigate a world of medium-sized objects moving at reasonable speeds. We never needed to understand what happens when you approach the speed of light or fall into a black hole. Einstein described gravity, not as a force pulling objects together, but as the geometry of space-time itself. Mass and energy tell space-time how to curve, and the curvature tells objects how to move. It's an elegant idea, but it requires you to imagine space itself having a shape, bending in directions we can't visualize because we're embedded within it. The usual demonstration involves pressing a bowling ball into a stretched rubber sheet and watching marbles roll around the depression. It's helpful up to a point, but it misleads us too. The rubber sheet analogy suggests space-time curves into some higher dimensional space, like a sheet bending downward. In reality, space-time curves through itself, which is much harder to picture. This difficulty with visualization reveals something deeper about the limits of human understanding. We're trying to comprehend something that operates on scales far removed from our everyday experience. Space-time behaves differently near black holes, where gravity becomes so intense that time nearly stops from an outside observer's perspective. It behaves differently at the quantum level, where the smooth fabric might break down into something granular and uncertain. At the largest scales, space-time carries galaxies apart as the universe expands. The space between distant galaxies grows, not because the galaxies are moving through space, but because space itself stretches. New space appears between them, like dots drawn on a balloon that separate as you inflate it. This expansion means that light from distant galaxies gets stretched, too, shifting toward redder wavelengths as it travels through expanding space to reach our telescopes. The more we probe spacetime, the stranger it becomes. Near the event horizon of a black hole, the normal relationship between space and time breaks down. Time dilates so severely that someone falling in would appear to freeze at the edge from an outside observer's view, their image gradually fading and reddening. But from the perspective of the person falling, they pass through normally, at least until they encounter other extreme effects closer to the singularity. Quantum mechanics adds another layer of mystery. At the smallest scales, spacetime might not be smooth at all, but foamy, fluctuating, uncertain. Virtual particles pop in and out of existence, borrowing energy from the vacuum and paying it back so quickly that the universe's bookkeeping can't keep track. This quantum foam suggests that the very concepts of space and time might emerge from something more fundamental, the way wetness emerges from water molecules. The search for a theory of quantum gravity tries to reconcile these different pictures, the smooth, curved spacetime of general relativity with the discrete, probabilistic world of quantum mechanics. String theory proposes that fundamental particles are tiny vibrating loops in higher dimensional spaces. Loop quantum gravity suggests spacetime itself is made of discrete units, like pixels in a cosmic display. But these approaches remain incomplete, mathematical frameworks without definitive experimental confirmation. Perhaps our struggle to understand spacetime reflects something profound about consciousness itself. We exist as patterns of matter and energy embedded within spacetime, trying to comprehend the very thing that contains us. It's like asking a wave to understand the ocean, or a note to explain the symphony. Our thoughts arise from processes happening within spacetime, so using those thoughts to fully grasp spacetime might be fundamentally limited. The mathematics works beautifully, equations that predict and describe with remarkable precision. But mathematics and intuitive understanding are different things. You can calculate exactly how much time dilates at a given velocity, without feeling in your bones why time should slow down at all. The formulas capture the behavior without necessarily revealing the deeper nature of what's happening. This gap between calculation and comprehension might be permanent, or it might simply reflect our current stage of understanding. Children learn to use smartphones without understanding semiconductor physics. Maybe we're learning to use spacetime through our equations and experiments, while the deeper understanding waits for future insights, new ways of thinking that we haven't developed yet. The universe seems indifferent to our cognitive limitations. Spacetime continues to curve and flex and expand whether we understand it or not. Stars form and die, black holes merge and send ripples across space. Galaxies dance their slow gravitational ballet. Our understanding follows behind, approximating and modeling, and gradually improving, but always chasing something that remains partially beyond our grasp. Physics has this strange way of hiding its most fundamental secrets behind things that seem perfectly ordinary. Every morning you wake up, your feet find the floor, gravity pulls you downward, in a predictable way. Time ticks forward at what feels like a steady pace. Yet beneath this everyday stability lies something so bizarre that even scientists struggle to wrap their heads around it. The fabric of reality itself, this thing we call spacetime, operates by rules that defy everything our senses tell us about the world. Your brain evolved to notice predators, find food, navigate familiar landscapes. It wasn't designed to comprehend structures that bend and twist in dimensions you can't see, or to grasp how time itself can speed up and slow down depending on where you happen to be standing. Think about holding a piece of stretchy cloth between your hands. Press your finger into it, the cloth dips. Stretch it, the pattern changes. This comparison gets thrown around a lot when people try to explain how massive objects warp space around them. But the comparison falls apart pretty quickly. That cloth has a resting shape. It sits in a particular direction. It depends on gravity to give it meaning. Spacetime doesn't rest on anything, doesn't sit inside some larger container. doesn't depend on forces from outside itself. The word fabric itself creates problems. Fabrics are woven from threads, built from smaller pieces you could theoretically pull apart. When we look at space-time through our most powerful instruments, it appears smooth, continuous, like a perfect sheet with no visible seams. Yet our theories hint that this smoothness might be an illusion, that if we could zoom in far enough, we might find something much more complex hiding beneath. This uncertainty points to one of the deepest puzzles in modern science. We have two incredibly successful theories that describe reality, but they refuse to work together. General relativity handles the big picture, the way planets orbit stars, how galaxies cluster together, the overall architecture of the universe. It treats space-time as smooth, geometric, predictable. Quantum mechanics takes care of the tiny scale, the realm of particles and probabilities and behaviors that seem to follow completely different rules. Both theories work brilliantly in their own domains. Put them together, especially in extreme places where space becomes incredibly curved and incredibly small, and the equations break down completely. It's like having two sets of perfectly good instructions that contradict each other the moment they overlap. This creates a scientific limbo that's both frustrating and fascinating. We know space-time exists. We can measure how it bends and stretches. We can detect the ripples that travel through it when massive objects collide, billions of light years away. But we don't know what it's actually made of, or whether it's made of anything at all. Some physicists imagine space-time as truly continuous, smooth all the way down to the smallest possible scales. Others propose it's granular, built from discrete pieces too tiny to detect with current technology. Still others think it might be emergent, arising from interactions between even more fundamental structures we haven't discovered yet. In this view, space-time becomes like a mirage, something that appears real but forms only when deeper, hidden components interact in complex ways. The philosophical implications are quietly staggering. If space-time is emergent, if it's not fundamental, but rather something that crystallizes out of more basic ingredients, then everything you think of as solid reality, every object, every moment, every memory, exists within what might essentially be a very convincing illusion. Testing these ideas pushes our technology to its absolute limits. It's one thing to study physics in a laboratory where distances are manageable and forces are controllable. It's quite another when your subject is the structure of the entire universe. You can't travel to a black hole to measure how severely it warps space. You can't rewind time to study what happened in the first moments after the Big Bang, when space-time itself was presumably being born. Instead, scientists work like cosmic detectives, gathering clues from incredibly subtle effects. They measure tiny distortions in laser beams caused by gravitational waves passing through Earth. They track how stars move near the supermassive black hole at the center of our galaxy. They study the way light bends as it travels past massive galaxy clusters. Each measurement tells us something about space-time, but only through the most delicate, indirect methods. It's like trying to understand the shape of some vast, invisible creature by studying only the ripples it makes as it swims past in dark water. You can learn quite a lot from those ripples if you're clever enough, but the creature itself remains hidden, known only through its effects. Our intuition, shaped by millions of years of evolution on a relatively stable planet, simply isn't equipped for this kind of thinking. Gravity feels constant here. Time seems to flow at a steady rate. Distances don't usually stretch or compress in noticeable ways. Space-time operates beyond these comfortable boundaries, in regimes where all our everyday assumptions break down. Even explaining space-time requires comparisons to things it decidedly is not. We call it a fabric, but it isn't cloth. We describe it as a grid, but no one drew those lines. We talk about it stretching, but stretching implies a material existing within some larger space. Space-time isn't inside anything else. It is the thing that everything else is inside of. This mismatch between what space-time actually is and what we can easily picture creates a permanent barrier to understanding. Yet somehow, That difficulty draws people back to the subject again and again. There's something deeply compelling about contemplating the structure that underlies all existence. Even when that structure refuses to fit neatly into familiar categories, every falling apple, every planetary orbit, every tick of your watch is shaped by spacetime's influence. We live immersed in it constantly, carried along by its subtle currents, yet we barely grasp its true nature. The very ground of reality remains mysterious, a reminder that the universe is far stranger and more wonderful than our everyday experience suggests. In the quiet hours when you're drifting towards sleep, when the busy thoughts of the day begin to settle, there's something oddly comforting about this cosmic uncertainty. The fact that scientists, with all their sophisticated instruments and elegant equations, still grapple with such fundamental questions. The universe keeps its deepest secrets well hidden, revealing them only gradually, one careful observation at a time. Perhaps that's how it should be. A reality that gave up all its mysteries too easily might be less interesting, less worthy of wonder. The ongoing puzzle of spacetime reminds us that we're still at the beginning of understanding, still learning how to ask the right questions about the strange, invisible architecture that makes everything else possible. Walking through your neighborhood, you're moving along paths carved by invisible forces. Every step you take follows rules you can't see, through a landscape that bends and curves in ways your senses never detect. The ground feels solid, predictable, but beneath that simple feeling lies one of the most profound mysteries in all of science. Space and time aren't separate things, like most people imagine. They're woven together into a single fabric, a structure that physicists call spacetime. This fabric surrounds everything, holds everything, and shapes the way everything moves. Yet we can't touch it, can't see it directly, can't feel it stretching or bending around us. Think about tossing a ball into the air. Your instinct tells you gravity pulls it back down, some invisible force yanking it toward the earth. But that's not really what's happening. The ball isn't being pulled at all. It's simply following the natural shape of spacetime itself, rolling along curves and contours that exist all around us, hidden from view. Einstein discovered that massive objects, like planets and stars, actually bend this fabric of spacetime. The Earth curves the space around it, creating invisible hills and valleys that guide everything from falling apples to orbiting satellites. The ball you threw isn't fighting against some mysterious force. It's taking the most natural path possible through a curved landscape you can't see. This gets strange very quickly. If Earth were more massive, time itself would run slower here. Your watch would tick differently. Your morning coffee would cool at a different rate. Your entire experience of duration would shift. But you'd never notice, because everything around you, including your own thoughts, would slow down together. Physicists often say something that sounds almost poetic. They say gravity isn't something you feel. What you feel is the effort required to resist falling deeper into spacetime's natural curves. When you're sitting in a chair right now, you're not resting peacefully. You're actually accelerating, pushing against the curved path that spacetime wants you to follow. Our brains didn't evolve to understand any of this. We developed senses that help us navigate surfaces, recognize shapes, judge distances in the immediate world around us. Evolution never required our ancestors to grasp cosmic-scale geometry. They needed to spot predators, find food, navigate familiar territories. Understanding the invisible architecture of the universe wasn't part of the survival toolkit. That's why this feels so counterintuitive. It's like trying to walk through a perfectly dark room where the floor slopes and curves in complex ways. You can't see the changes, so every unusual step feels like your own clumsiness rather than the environment shaping your movement. Space-time works the same way, guiding everything while staying completely invisible. Einstein's equations can describe all of this mathematically, with remarkable precision. They predict exactly how space-time curves around different masses, how time dilates near massive objects, how gravitational waves ripple outward when black holes collide. The math works beautifully, but understanding the calculations isn't the same as grasping what's really happening. If you ask why mass curves spacetime in the first place, or what spacetime is actually made of, or why this geometry takes the specific shapes it does, those questions remain mysteries. The equations tell us how everything behaves, but they don't reveal the deeper why behind it all. Something even stranger emerges when you realize that spacetime doesn't just respond to matter, it reacts to energy, pressure, motion, even empty space itself. Vacuum isn't actually empty, isn't just a blank background where things happen to exist. Empty space has structure, properties, the ability to stretch and change, even where there's absolutely nothing at all. The expansion of the universe demonstrates this perfectly. Distant galaxies aren't flying away from us like ships sailing across an ocean. The ocean itself, space-time, is expanding and carrying the galaxies along with it. This expansion doesn't need fuel, doesn't require engines pushing things apart. It's simply what spacetime does, a built-in behavior of the fabric itself. When we try to study something this elusive, we face unique challenges. You can push air and feel it, move, heat metal, and watch it expand, stretch a rubber band, and sense its resistance. But spacetime doesn't resist when it's stretched. It doesn't push back, doesn't create pressure you can measure with ordinary instruments. It simply changes, and the only evidence of the change is the movement of whatever sits within it. This means we're always studying spacetime indirectly, watching its effects, rather than observing the thing itself. It's like trying to understand wind by watching leaves dance in a tree. You see the consequences clearly, but the cause remains invisible, known only through its influence on everything else. Spacetime also turns out to be remarkably dynamic. It's not a fixed container, holding the universe like water in a bowl. It evolves constantly, ripples with waves, interacts with everything it contains. When massive black holes spiral into each other and merge, the collision sends gravitational waves racing outward at the speed of light. These waves stretch and compress space itself as they pass through everything in their path. We've actually detected these waves using incredibly sensitive instruments. The measurements match Einstein's predictions with stunning accuracy. But detecting something doesn't automatically make it feel intuitive. When a gravitational wave passes through your body, you don't feel anything unusual. You don't sway, don't sense any change. Yet the wave is real, briefly altering the geometry of space around you. Time adds another layer of complexity to this picture. We experience time, but not in any consistent way. Minutes can feel like hours during boring meetings. Hours can flash by like minutes when you're absorbed in something fascinating. The fact that space-time weaves this subjective elastic experience of time together with the three dimensions of space creates a structure that defies easy visualization. If space-time were just space, we might picture it as a landscape with hills and valleys. But when time becomes part of the geometry, when the flow of time itself can speed up or slow down depending on gravity and motion, the structure becomes something much more complex. It's like a living map that redraws itself for every observer, showing different features to different travelers. This brings us to one of the most mind-bending aspects of the whole picture. Spacetime doesn't hold everything together the way glue binds paper, or the way a spider's web traps insect. Instead, it holds everything together by establishing the fundamental rules for how motion works, how events unfold, how cause and effect play out across the universe. The curvature of spacetime determines which paths objects can follow. The flow of time determines the sequence in which events occur. Together, they create a coherent universe. Even though that coherence operates through principles completely hidden from our direct experience. We're used to thinking about space as something we move through, like walking across a field. We think about time as something that measures change, like a clock counting seconds. But spacetime is both simultaneously a place and a process, a map and a timeline, a geometry and a rhythm, all woven into one unified structure. Our minds don't naturally blend these concepts together. It requires a kind of mental flexibility that doesn't come easily, even to physicists who work with these ideas every day. That's part of what makes spacetime feel so mysterious and beautiful at the same time. It's everywhere around us, shaping every aspect of reality, yet it never announces its presence. It works quietly, invisibly, like a stage manager coordinating a cosmic performance. From behind curtains, we can never pull aside. Every motion, every interaction, every moment of existence unfolds according to its hidden choreography. Perhaps that's what makes exploring these ideas so fascinating. We're investigating something that's simultaneously the most intimate part of our experience and the most remote mystery in science. Every breath you take, every thought, happens within this invisible architecture. Yet understanding even the basics requires us to abandon our most fundamental assumptions about how reality works. The universe operates on principles far beyond what our senses can directly detect. That gap between experience and reality is where science becomes almost philosophical, pushing us to imagine structures and processes that exist beyond the reach of intuition, yet somehow give rise to everything we know and are. Some ideas in science slip into our minds effortlessly, while others remain forever elusive, no matter how many times we encounter them. Einstein's vision of spacetime belongs firmly in that second category. You might read about it, watch explanations, listen to lectures, yet something always feels just out of reach. This isn't about intelligence or imagination failing us. It's woven into the very nature of what Einstein discovered. Our brains evolved to navigate a world of medium-sized objects moving at moderate speeds. We developed intuitions about space being a container, time flowing like a river, gravity pulling things downward. These aren't learned concepts from textbooks. They emerge from countless moments of living. Dropping a cup, walking across rooms, waiting for events to unfold. Every experience reinforces the idea that space stays put. Time marches steadily forward, and massive objects simply attract smaller ones. Then Einstein arrives with news that overturns these foundations. Space curves, time stretches, gravity isn't a force but geometry itself. The universe operates according to principles that have no counterpart in human experience. We never move fast enough to notice time dilation. We don't live near objects massive enough to visibly warp space-time. Our daily reality gives us no preparation for these revelations. Consider the speed of light remaining constant, regardless of motion. When you throw a ball from a moving car, common sense says it travels faster than a ball thrown while standing still. Light refuses to follow this pattern, no matter how quickly you move toward or away from a light source. Photons always zip past at exactly the same speed. Since light won't budge from its cosmic speed limit, something else must give way. That something turns out to be space and time themselves, stretching and compressing to maintain light's stubborn consistency. This creates a peculiar mental challenge. Most understanding comes from recognizing patterns we've encountered before. Stack blocks, learn about solidity. Pour water, discover flow. Spin in circles, experience dizziness and motion. But Einstein's universe operates in regimes completely foreign to human senses. We have no direct experience with relativistic speeds, extreme gravitational fields, or four-dimensional geometry. Our pattern recognition machinery simply lacks the raw material to build intuitive understanding. The explanations we typically hear rely on simplified metaphors. Rubber sheets with bowling balls, fabric stretching underweight, clocks ticking at different rates. These comparisons offer glimpses of the underlying reality, but they're necessarily incomplete. They give us something familiar to hold on to, yet the familiar elements behave in unfamiliar ways. When our brains encounter something that looks recognizable but follows alien rules, confusion often results. Time dilation provides a perfect example. You can understand the explanation intellectually. Moving clocks run slower. Clocks in stronger gravitational fields run slower. The mathematics works out. The experiments confirm it. GPS satellites require corrections for it. But unless you've personally experienced time passing differently, the concept remains purely theoretical. Believing something and feeling it intuitively are entirely different mental states. Einstein also demolished our notion of universal simultaneity. We naturally assume everyone everywhere experiences the same now, Despite knowing about time zones and Earth's rotation, relativity reveals this as illusion. What counts as simultaneous depends on motion. Two observers moving relative to each other can legitimately disagree about whether distant events occurred at the same moment. Neither observer is wrong. Simultaneity simply isn't absolute. This strikes at something fundamental about our place in the cosmos. We imagine ourselves embedded in a universal present moment, connected to everyone else through shared time. Relativity suggests this connection is more fragile and observer-dependent than we'd like to believe. The present moment becomes a personal, local phenomenon rather than a cosmic absolute. Another unsettling aspect involves the theory's silence about underlying mechanisms. Einstein's equations describe how mass and energy curve spacetime, how that curvature guides motion, but they don't explain why the universe operates this way. It's like having a perfect map of a city without knowing who built it or why the streets follow their particular paths. The mathematical description works flawlessly for making predictions, yet leaves deeper questions unanswered. Visualizing spacetime curvature presents additional obstacles. Most diagrams show two-dimensional surfaces bending in familiar three-dimensional space, but real spacetime is four-dimensional, curving in ways that have no analog in everyday geometry. We see the diagram and interpret it like hills or valleys, solid surfaces deforming under weight. The actual curvature Einstein describes is pure geometry, mathematics made manifest in the structure of reality itself. Our minds try to picture something bending without bending into anything else, curving without having anywhere to curve into. This challenges spatial reasoning in ways we're simply not equipped to handle. The visualizations serve as useful calculational tools, but they can't bridge the gap to genuine comprehension. Einstein's elimination of gravitational force adds another layer of conceptual difficulty. Forces feel intuitive. Push something, it moves. Drop something, gravity pulls it down. But in Einstein's picture, objects follow natural paths through curved spacetime. What we experience as gravitational force is really the sensation of resisting that natural motion. Standing on Earth's surface, we're constantly accelerating upward relative to our natural trajectory through spacetime. This inverts our usual understanding of cause and effect. Instead of gravity causing spacetime to curve, the curvature is gravity. Mass and energy don't create forces that pull objects around. They reshape the geometric stage on which motion unfolds. Objects then follow the straightest possible path through this curved arena. When you try to explain motion using shapes rather than forces, it demands a fundamental shift in thinking. Even physicists who've spent careers working with relativity often admit that certain aspects still feel strange conceptually. The mathematics flows beautifully. Experiments confirm predictions with extraordinary precision. Practical applications work perfectly. Yet the underlying picture can remain difficult to internalize completely. It's like learning a second language as an adult. You might achieve fluency, but your native tongue often still feels more natural. Perhaps this persistent sense of unfamiliarity isn't a bug, but a feature. Einstein revealed that the universe operates in ways profoundly different from human intuition suggests. The fact that his discoveries still feel surprising after more than a century might simply reflect how successfully he transcended the limitations of everyday experience. Some truths about reality may be too alien to ever feel completely comfortable to minds shaped by life in this particular corner of space-time. We tend to think of ourselves as creatures who understand the world around us pretty well. After all, we walk through space, we experience time passing, we see objects move from one place to another. Everything seems straightforward enough, but there's something unsettling about discovering that this everyday experience, the one we trust completely, might only be showing us a tiny slice of what's actually happening. When we were children, most of us learned that the world worked in simple ways. Things fall down, not up. Time moves forward at the same pace for everyone. Space is just empty room where things happen. These ideas felt natural because they matched what we could see and touch and feel. They became the foundation for how we picture reality. The strange thing is, These simple rules actually work perfectly well for almost everything we encounter in daily life. If you're driving a car or throwing a ball or planning when to meet a friend, Newton's old physics gives you exactly the right answers. The moon orbits Earth in predictable ways. Bridges stay up, clocks keep time. Everything behaves just the way you'd expect. But then science started looking more carefully at things that move very fast, or things that are incredibly massive, or light itself. And that's where the comfortable picture began to break down. It turned out that the universe had been keeping some pretty big secrets. Light, for instance, does something that shouldn't be possible. According to our everyday understanding, no matter how fast you're moving when you measure the speed of light, you always get the same answer. This is completely unlike anything else we experience. If you're in a moving car and another car passes you, its speed depends on how fast you're going, but light doesn't work that way. Whether you're standing still or flying through space, light always appears to move at the same speed. This discovery created a puzzle that scientists couldn't ignore. Either their measurements were wrong, which seemed unlikely after many careful experiments, or something fundamental about motion and time and space wasn't what people thought it was. The solution, when it finally came, was both elegant and deeply strange. Space and time, it turned out, aren't separate things. They're woven together into a single fabric that can stretch and bend and curve. When you move very fast, time actually slows down for you, compared to someone who's standing still. When you're near something incredibly massive, like a star, both space and time get warped by the gravitational field. These aren't just mathematical curiosities. They're real effects that we can measure with precise instruments. Satellites orbiting Earth have to account for the fact that time runs slightly differently up there compared to down here. Without those corrections, GPS systems would give you directions to the wrong location. There's something almost philosophical about this situation. We evolved to survive in a world of moderate speeds and moderate gravitational fields. Our senses, our intuitions, our ways of thinking about cause and effect, all developed in an environment where space seemed flat and time seemed steady. We never had any reason to suspect that reality might be far more flexible than it appeared. In a way, it's similar to how people once believed the Earth was flat. From their perspective, standing on the surface, that conclusion made perfect sense. The ground looked flat. Walking in a straight line felt like walking in a straight line. It wasn't until people started traveling very long distances and making careful observations of ships and stars that the curvature became obvious. The difference is that with space and time, the effects are much more subtle in everyday life. You'd have to be moving at a significant fraction of the speed of light, or hanging out near a black hole before the warping became something you could feel directly. So we're in this odd position where our most fundamental ideas about reality are based on a very limited sample of possible experiences. This creates a kind of disconnect between what we know intellectually and what we feel intuitively. You can learn about time dilation and curved spacetime. You can see the mathematical proofs. You can understand how GPS satellites work. But some part of your mind still expects time to flow at the same rate everywhere, and space to be the simple, empty container you grew up imagining. That tension isn't necessarily a bad thing. It's a reminder that the universe is far more interesting and complex than our everyday experience suggests. There are layers of reality operating beyond what our senses can detect directly. Black holes exist where spacetime curves so severely that not even light can escape. Gravitational waves ripple across the universe when massive objects accelerate. The expansion of space itself carries distant galaxies away from us faster than the speed of light. Each of these phenomena pushes us further away from the comfortable, intuitive picture of reality we started with. They ask us to accept that the universe operates according to rules that feel foreign and mathematical and abstract. Rules that we can verify and use and build technology around, but that never quite feel natural in the way that throwing a ball or watching a clock feels natural. There's something humbling about this realization. For most of human history, people assumed that the way things appeared to them was pretty close to the way things actually were. The sun seemed to revolve around the Earth. So that's what people believed. Objects at rest seemed to want to stay at rest unless pushed. So that became a rule. Time seemed to flow at the same rate everywhere, so that became part of the foundation of physics. But each of these assumptions eventually had to be revised as better tools and more careful observations revealed hidden complexities. The pattern suggests that our current understanding, as sophisticated as it might seem, probably still contains blind spots and limitations that we haven't discovered yet. Modern physics has opened doors to questions that become stranger the more deeply you explore them. What happens at the center of a black hole, where mathematical equations suggest space-time curvature becomes infinite? How did time itself begin, if it began at all? Are there other dimensions of space that we simply can't perceive? Could time flow differently in other parts of the universe? These aren't just academic puzzles, they're invitations to expand our conception of what's possible. They remind us that reality extends far beyond the narrow slice we experience directly. And they suggest that some of the most important truths about the universe might be hiding in places where our intuition simply can't reach. The remarkable thing is that despite all this strangeness, despite all the ways that modern physics challenges our everyday assumptions, the mathematics works beautifully. The equations are elegant. The predictions match experiments with extraordinary precision. There's a deep harmony underlying all the apparent weirdness, a consistency that suggests we're uncovering something genuinely true about how reality operates. Maybe that's the most profound lesson of all. The universe doesn't owe us explanations that feel comfortable or intuitive. It doesn't have to match our expectations or conform to the limitations of our senses. It simply is what it is, following its own internal logic, operating according to principles that we're still learning to understand. And perhaps there's something beautiful about that mystery. Something that keeps pulling us deeper into questions we never thought to ask. When physicists first started thinking about time and space, they pictured them as fixed backdrops, unchanging stages where events played out. Time ticked forward at a steady pace everywhere. Space stretched out in straight lines, never wavering. This seemed obvious because that's how our everyday world appears to work. But appearances, as we've learned, can be deeply misleading. The revolution in our thinking began when scientists examined what happens to objects moving at incredible speeds. As something approaches the speed of light, something strange occurs. Time actually begins to slow down for that moving object. The effect isn't just theoretical, it's measurable. A clock racing through space at near light speed would tick more slowly than an identical clock sitting still. Length changes too. Objects contract, becoming shorter in the direction they're moving. Again, this isn't some illusion or trick of measurement. The contraction is real. These changes stay hidden in our daily lives because we move so slowly compared to light. A car speeding down a highway experiences these effects, but they're so tiny that no instrument we have could detect them. This flexibility of time and space opened up a completely different way of thinking about reality. If motion could stretch and compress the very fabric of existence, then maybe that fabric wasn't as solid as everyone had assumed. Maybe it was more like a malleable material, something that could be shaped and molded. The next leap came from reconsidering gravity itself. For centuries, gravity had been understood as a force, an invisible hand pulling objects toward each other. Apples fall from trees because Earth pulls them down. Planets orbit the sun because the sun's gravity tugs on them. This picture worked beautifully for most situations, accurately predicting the motion of everything from cannonballs to comets. But what if gravity wasn't really a force at all? What if it was something entirely different? This question led to one of the most elegant insights in all of physics. Instead of thinking of gravity as a pull, imagine it as the shape of space and time themselves. Picture rolling a marble across a perfectly flat table. The marble travels in a straight line. Now imagine the table has a gentle slope or a curved depression. The marble still follows the most natural path available, but that path is no longer straight. The marble isn't being pushed or pulled in any mysterious way. It's simply responding to the geometry of the surface it's rolling on. Space and time work similarly around massive objects. A star or planet doesn't pull on nearby objects with some invisible force. Instead, the star's mass changes the shape of space-time around it. Objects moving through that region follow the curves and contours that the mass has created. What we experience as gravity is really just objects following the most natural paths through curved space-time. This insight transforms our understanding of falling. When you drop a stone, it doesn't fall because Earth pulls it down. The stone follows a straight path through space-time that happens to be curved by Earth's presence. From the stone's perspective, it's moving in a perfectly straight line. The curvature of space-time makes that straight line appear curved to us. The curvature affects more than just motion through space. Time itself becomes part of the geometry. In regions where space-time curves more steeply, time runs slower. Near massive objects, clocks tick at different rates depending on their position. This isn't a malfunction of the clocks. Time genuinely flows at different speeds in different locations. Scientists have tested this prediction with remarkable precision. Two atomic clocks, identical in every way, tick at measurably different rates when placed at different heights. The difference is tiny, but it's exactly what the mathematics predicts. Time literally stretches and compresses based on the gravitational environment. Light also follows these curved paths through space-time. When starlight passes close to the sun, it bends slightly, following the curvature that the sun's mass creates. During solar eclipses, when the sun's bright light is blocked, astronomers can observe this bending directly. The measurements match theoretical predictions with stunning accuracy. These discoveries reshape how we think about the universe's fundamental structure. Rather than seeing space as an empty container holding objects that push and pull on each other, we find a dynamic fabric where geometry itself drives the behavior of matter and energy. Mass and energy tell space-time how to curve. The curvature tells objects how to move. This geometric view of gravity leads to some of the most extreme predictions in physics. Black holes represent regions where space-time curves so dramatically that nothing, not even light, can escape once it crosses a certain boundary. Near these objects, time slows so severely that distant observers would see clocks nearly freeze, even though someone falling in would experience time normally. The curvature of space-time responds to more than just the mass of stars and planets. Energy in any form contributes to the shape. Moving objects, pressure, radiation, even the energy that seems to fill apparently empty space, all play a role in determining geometry. Recent observations suggest that empty space itself contains a form of energy that's causing the entire universe to expand at an accelerating rate. This reveals space-time as an active participant in cosmic events, rather than a passive backdrop. The fabric of reality has its own properties and behaviors. It can ripple and wave when massive objects accelerate. It can stretch as the universe expands. It responds dynamically to the energy and matter it contains. The strangeness of these ideas reflects how limited our everyday experience really is. We live in a narrow slice of reality, where speeds are low, gravitational fields are relatively weak, and distances are small. In this comfortable zone, space-time appears rigid and unchanging. But step outside these familiar conditions, and the true flexibility emerges. Our minds evolve to navigate a world where time flows steadily and space extends in straight lines. We never developed intuitions for environments where these assumptions break down. Yet the universe operates according to principles that remain perfectly consistent, whether or not they align with human intuition. The mathematical descriptions of curved spacetime are precise and unambiguous. The experimental tests confirm the predictions again and again, but translating these mathematical truths into mental pictures that feel natural remains challenging. We're forced to expand our conception of what's possible, to accept that reality operates in ways that transcend our built-in expectations. Perhaps that's part of what makes these discoveries so profound. They remind us that the universe doesn't conform to human limitations. It follows deeper patterns that reveal themselves only through careful observation and mathematical analysis. The bending of space and the stretching of time aren't aberrations or curiosities. They're fundamental features of the reality we inhabit, hidden from casual view but always present. shaping every moment and every motion in ways both subtle and profound. When we look up at the night sky, there's something deeply satisfying about thinking the universe follows clear, simple rules. Stars move in predictable paths, galaxies spin with apparent order, and everything seems to follow patterns we can measure and understand. Einstein's theory of relativity captures this beautifully, describing how massive objects bend the fabric of spacetime itself. Picture a bowling ball placed on a stretched rubber sheet. The heavy ball creates a dip, and if you roll marbles nearby, they curve toward that depression. This is essentially how gravity works according to relativity. Planets orbit stars, light bends around massive objects, and time itself runs slower in strong gravitational fields. When astronomers point their telescopes at distant galaxies or detect gravitational waves from colliding black holes, the measurements match Einstein's predictions with remarkable precision. But here's where things get philosophically interesting. The universe that works so elegantly on large scales operates by completely different rules when you zoom in. At the level of atoms and subatomic particles, quantum mechanics takes over, and it paints a very different picture of reality. Instead of smooth, predictable curves, the quantum world is full of uncertainty and constant fluctuation. Particles don't have definite positions until you measure them. Energy levels jump in discrete steps, rather than flowing continuously. Everything exists in a state of probability until observation forces it to choose a specific outcome. Now, you might think these two descriptions could coexist peacefully. After all, we use different tools to fix cars than we do to perform surgery. But physics doesn't work that way. The universe should follow one consistent set of rules, whether we're looking at galaxies or electrons. This creates a fascinating puzzle. Relativity insists that spacetime is smooth and continuous. Like a perfectly woven fabric, quantum mechanics suggests that nothing in the universe can be truly continuous. Everything should fluctuate and jitter at the smallest scales. If spacetime is just another physical field, it should be subject to quantum uncertainty too. The tension becomes most obvious in extreme situations where both theories should apply simultaneously. Black holes are perfect examples. According to relativity, matter falling into a black hole eventually reaches the center, where it gets compressed into a point with infinite density. This is called a singularity, and it's where Einstein's equations essentially throw up their hands and say, "I give up." Quantum mechanics doesn't like infinities either. It has built-in limits that prevent physical quantities from becoming infinite. So when you ask, what really happens at the center of a black hole, you get two different answers that can't both be correct. The same problem appears when physicists try to understand the very beginning of the universe. Rolling the clock backward, relativity can describe how the universe expanded from an incredibly hot, dense state. But push too far back, and the theory points toward another singularity, another moment where the math breaks down. It's like having two excellent roadmaps that cover different regions perfectly, but when you try to connect them, the highways don't line up. The scale is wrong, the landmarks don't match, and you're left with a frustrating gap right where you need to travel. This mismatch reveals something profound about our current understanding. We have two extraordinary successful theories, each verified by countless experiments and observations, yet they seem to describe different universes. One universe is smooth and deterministic, where effects follow causes in predictable ways. The other universe is grainy and probabilistic, where certainty dissolves into quantum foam. Perhaps the most humbling aspect of this situation is that it highlights the limits of our current perspective. We tend to assume that understanding nature means building better and better approximations, getting closer to some final truth. But what if the problem isn't that our theories are incomplete? What if the problem is that we're asking the wrong questions? Consider the deeper mystery of why mass and energy bend spacetime in the first place. Relativity describes this relationship beautifully, providing equations that predict exactly how much curvature different amounts of matter will create. But it doesn't explain the underlying mechanism. Why does spacetime respond to matter at all? What is it about the presence of energy that causes geometric distortion? It's similar to knowing that pressing a light switch turns on a bulb, without understanding electricity. The relationship works perfectly every time, but the deeper why remains hidden. This suggests that spacetime's behavior might be a symptom of something even more fundamental that we haven't discovered yet. Then there's the question of spacetime's true nature. At the scales we can observe, it appears perfectly smooth, like a continuous sheet extending in all directions. But quantum mechanics hints that this smoothness might be an illusion, similar to how a sandy beach looks uniform from an airplane, but reveals its granular structure up close. Some theories propose that spacetime itself might be made of tiny, discrete units, far smaller than atoms or any particles we've detected. If this is true, then the smooth geometry of relativity would be like the surface of a calm ocean, appearing continuous from a distance but actually composed of countless individual water molecules. Our current instruments aren't nearly sensitive enough to detect such fine structure, if it exists. We're essentially trying to determine whether sand is made of individual grains by looking at it from space. The uncertainty leaves us with another piece of the puzzle that doesn't quite fit with the others. This incompleteness isn't necessarily frustrating, though. It's more like standing at the edge of a vast unexplored territory, knowing that the most interesting discoveries probably lie just beyond our current maps. The fact that our two best theories disagree so fundamentally suggests that something remarkable is waiting to be understood, something that will likely change our entire perspective on reality. Think about temperature for a moment. You can't find temperature in a single atom, no matter how hard you look. But get enough atoms moving around together, and suddenly temperature emerges from their collective dance. Some physicists wonder if spacetime works the same way. Maybe spacetime isn't the fundamental foundation we think it is. Maybe it's more like temperature, emerging from something deeper. When you get enough of those deeper ingredients together, picture the universe as containing some basic components we haven't identified yet. When these components gather in large enough numbers, they create what we experience as space-time. This would mean that at the tiniest scales, space-time might not exist at all. Only when enough of these mysterious building blocks come together would the familiar fabric of space and time appear. It's a captivating idea, but it opens up more questions than answers. What exactly are these underlying ingredients? How do they manage to create the geometry we see around us? And why does that geometry follow the specific rules it does? These questions point to gaps in our understanding that feel both frustrating and exciting. Empty space presents another puzzle that doesn't want to be solved. Quantum mechanics tells us that what we call empty space is actually buzzing with activity. Tiny fluctuations of energy pop into existence and vanish again, constantly. It's like the universe has a case of energetic hiccups that never stops. When physicists try to calculate how much energy all these fluctuations should add up to, they get a number so large it defies belief. The calculation suggests empty space should contain enough energy to either crush the universe into a point or make it expand so fast that everything gets ripped apart instantly. But neither of those things happens. The universe expands at a perfectly reasonable rate. Thank you very much. This creates what some call the biggest disagreement between theory and reality in the history of physics. The numbers are off by an amount so huge it's almost embarrassing. According to relativity, energy curves spacetime. If empty space really contained as much energy as quantum mechanics predicts, spacetime would bend into impossible shapes. Something has to be wrong, either with the quantum calculation or with how we think energy affects geometry. Dark energy adds another layer of confusion to the mix. Observations show that the universe's expansion is speeding up over time, not slowing down like you might expect. Relativity can account for this behavior if you add a special term to the equations, something that acts like a repulsive force spread throughout space. The math works, but nobody knows what this dark energy actually is. We can measure what it does, we can describe its effects with equations, but its true nature remains completely mysterious. It seems to be built into the fabric of space-time itself, like a property of geometry that we never saw coming. The problem is that dark energy doesn't play nicely with quantum predictions, and it doesn't match anything we've created in laboratories. It sits awkwardly between our theories, like a piece from a different puzzle that somehow ended up in our box. Dark matter creates a different kind of headache. When astronomers look at galaxies, they find something strange. The stars at the edges of these galaxies move much faster than they should, based on all the visible matter they can see. These stars should be flying off into space, but they're not. Something invisible must be providing extra gravitational pull to keep everything together. The most straightforward explanation is that there's a lot of matter out there we simply can't see, but none of the particles we know about, or even the ones we've predicted, fit the behavior perfectly. Relativity explains how this invisible mass would bend spacetime, but the actual identity of the mass remains a complete mystery. It's like having the shadow of something without knowing what's casting it. Time itself creates tension between our theories. In relativity, time gets woven into spacetime as just another dimension. You can't separate time from space, they're part of the same fabric. But quantum mechanics treats time differently. Time stays on the sidelines, like a clock ticking in the background, while quantum events unfold. This mismatch creates real problems. How can time be part of spacetime in one theory but a separate entity in another? The two pictures simply don't line up, and until they do, any attempt to unify them remains incomplete. Even the way forces work reveals this split personality in physics. Relativity describes gravity not as a force at all, but as the curvature of space-time. Mass and energy bend the fabric, and objects follow the curves. Meanwhile, quantum mechanics describes all the other forces using particles and fields. Trying to force gravity into the quantum framework leads to mathematical disasters. The equations blow up or collapse into meaningless results. Attempting to treat space-time as just another field sitting on top of some fixed background doesn't work either. Because space-time is the background, these failures aren't really failures at all. They're clues pointing towards something larger that we haven't grasped yet. Each mathematical wall we hit tells us that the puzzle extends beyond the pieces we currently have. Locality presents another fascinating mismatch. Relativity insists that nothing can influence anything else faster than the speed of light. It's a cosmic speed limit that seems absolute. But quantum mechanics allows entangled particles to show instant correlations across vast distances. These correlations don't actually send information faster than light, so relativity isn't technically broken. But the deeper explanation for how this works remains unclear. Does space-time have some hidden structure that allows this instant coordination? Or do these correlations hint at something that exists outside space-time entirely? All these mismatches create a peculiar situation in physics. We have a beautifully clear picture of how things work on large scales, and an equally clear picture for small scales. But these two pictures refuse to merge into one coherent view. They stand side by side, each accurate within its own territory, but unable to overlap smoothly. It makes spacetime feel incomplete, like we're working with tools designed for different jobs that haven't been combined into a unified toolkit. Yet, rather than discouraging scientists, these gaps and contradictions fuel deeper exploration. Each unexplained result, each mathematical breakdown, each theoretical mismatch points toward new territory, waiting to be discovered. At the smallest levels of reality, something strange happens to the rules we think we understand. The world of atoms and particles operates in ways that seem completely disconnected from the larger universe around us. When you look at everyday objects, things behave predictably. They stay where you put them. They follow clear paths. They respond to forces in ways that make sense. But shrink your view down far enough and all that reliability disappears. The quantum realm operates like it's reading from a completely different instruction manual. Particles don't sit in definite locations the way a coffee cup sits on a table. Instead, they exist as clouds of possibility, spread out across multiple potential positions until something forces them to choose. It's not that we simply don't know where they are. It's that they genuinely don't have a specific location until the moment we measure them. This creates one of the most unsettling discoveries in modern physics. the built-in uncertainty that governs tiny particles. The more precisely you try to pin down exactly where a particle is, the less you can know about how fast it's moving. And the reverse holds true as well. Know the speed perfectly, and the location becomes completely unclear. This isn't a limitation of our measuring tools. It's woven into the fabric of reality itself. Meanwhile, the larger universe operates on completely different principles. Massive objects bend the geometry of space and time in smooth, predictable ways. A planet follows a clear orbital path because it's moving along the curves created by the sun's gravity. There's no uncertainty here, no probability clouds, no mysterious jumps from one state to another. Everything flows according to geometric relationships that can be calculated with precision. These two descriptions of the same universe refuse to work together. It's like trying to solve a jigsaw puzzle, where half the pieces keep changing shape when you're not looking. The smooth curves of space and time don't account for the jittery, unpredictable behavior of quantum particles. And quantum mechanics doesn't explain how its random probabilistic rules somehow give rise to the orderly geometric patterns we see at larger scales. One of the most bewildering quantum behaviors involves particles acting as both waves and particles simultaneously. Send electrons through two narrow slits, and they create the kind of interference pattern you'd expect from waves, with alternating bands of light and dark. But try to peek and see which slit each electron actually passes through, and the wave pattern vanishes. And brain bid, the particles suddenly behave like discrete objects following individual paths. The act of observation itself changes the outcome. Before measurement, the electron somehow travels through both slits at once, interfering with itself to create the wave pattern. But the moment you try to catch it in the act, it collapses into being just a particle, taking just one path. The universe seems to maintain multiple possibilities, right up until the moment someone asks for a definite answer. This dual nature has no equivalent in the world of space-time geometry. Curved space doesn't suddenly decide which path an object will follow only after someone observes it. The gravitational relationships between masses create clear, predictable trajectories that exist whether anyone is watching or not. But quantum mechanics operates on probabilities that remain suspended in a strange state of multiple realities until measurement forces a choice. Even stranger is the phenomenon called quantum entanglement. When two particles interact in certain ways, they become linked in a connection that persists. No matter how far apart they travel, measure one particle and find it spinning in a particular direction, and instantly, without any signal passing between them, its partner will be found spinning in the opposite direction. The correlation appears to happen faster than light could travel between the particles. This creates a direct conflict with one of the most fundamental rules of relativity. Nothing can influence anything else faster than the speed of light. Yet quantum entanglement produces correlations that seem to ignore distance entirely. The particles remain connected as if space itself doesn't exist between them. This raises uncomfortable questions about whether quantum connections operate within space and time, or somehow outside of it entirely. If these correlations happen within our normal space-time, then they violate the speed of light limit. But if they happen outside of space-time, what does that even mean? Does the universe contain some deeper level of reality that underlies the space and time we experience? Or do the smooth geometric rules of relativity simply break down at quantum scales, applying only to larger objects and greater distances? Even empty space refuses to behave simply at quantum levels. What appears to be a perfect vacuum actually sees with constant activity. Quantum fields fluctuate continuously, causing pairs of particles to pop into existence and vanish again in tiny fractions of a second. The universe never sits completely still, even in regions that contain no matter or energy that we can directly observe. Relativity describes empty space as a smooth background that can stretch and bend, but it doesn't account for this constant quantum jitteriness. And when physicists try to calculate how much energy all these vacuum fluctuations should contribute, the numbers come out absurdly large. If the calculations were correct, space-time would curve so dramatically that the entire universe would either collapse immediately or expand so rapidly that no structures could ever form. Since that clearly doesn't happen, something is fundamentally wrong with how we're trying to combine these theories. The treatment of time creates another major incompatibility. In relativity, time is part of the flexible geometry of space-time. It flows at different rates depending on how fast you're moving and how close you are to massive objects. Time can stretch, compress, and even theoretically loop back on itself under extreme conditions. It's a dynamic dimension that responds to the presence of matter and energy. But quantum mechanics treats time as a fixed backdrop, a universal clock that ticks forward at the same rate for all quantum systems. There are no time dilations, no relativistic effects, no geometric relationships involving time in the basic quantum equations. Time just marches steadily forward while quantum probabilities evolve according to their own separate rules. This mismatch creates a fundamental problem. If time is part of space-time, and space-time can curve and stretch, then time should be flexible in quantum systems too, but quantum mechanics doesn't allow for that flexibility. It needs time to behave like a rigid parameter that never changes its rate or direction. The two theories demand incompatible versions of time itself. Attempts to describe gravity using quantum principles run into even more severe difficulties. The other fundamental forces, electromagnetism, the strong nuclear force, and the weak nuclear force, can all be understood in terms of particles that carry the force between objects. Photons carry electromagnetic force, gluons carry the strong force, and W and Z bosons carry the weak force. Following this pattern, gravity should be carried by particles called gravitines. But when physicists try to build a quantum theory of gravities using gravitons, the mathematics becomes unmanageable. Calculations that should produce finite, meaningful answers instead spiral off toward infinity. The theory predicts infinite energies and infinite probabilities, which makes no physical sense. Every attempt to tame these mathematical monsters creates new problems elsewhere in the equations. The universe somehow manages to operate smoothly despite these theoretical conflicts. Quantum mechanics makes incredibly precise predictions about atomic behavior, chemical reactions, and the properties of materials. Relativity accurately describes the motion of planets, the behavior of GPS satellites, and the evolution of the cosmos as a whole. Both theories work magnificently within their respective domains, but they seem to describe two different universes that happen to coexist in the same space. At large scales, smooth geometry dominates and quantum effects fade into insignificance. At tiny scales, quantum uncertainty reigns supreme, while gravitational effects become negligible. The boundary between these domains remains mysterious, a no-man's land where neither theory feels entirely comfortable. This divide suggests something profound about the nature of reality itself. Perhaps the universe operates on multiple levels simultaneously, with different rules applying at different scales. Or perhaps our current theories, despite their remarkable success, are still incomplete approximations of a deeper truth that unifies quantum behavior and space-time geometry in ways we haven't yet discovered. The search for that unifying principle continues to drive theoretical physics forward, pushing scientists to imagine new mathematical structures and exotic possibilities that might bridge the gap between the quantum and the cosmic. When we look at the universe around us, we find ourselves caught between two completely different ways of understanding reality. On one side, we have this beautiful, smooth picture where space and time flow together like a gentle river. On the other side, we have this wild, chaotic quantum world where nothing seems to follow the rules we expect. Gravity presents us with a peculiar puzzle. Unlike the other forces in nature, it refuses to play nicely with quantum mechanics. When physicists try to merge these two worlds, they run into mathematical problems that simply won't go away. Numbers become infinite, equations break down, and the elegant formulas that work everywhere else suddenly stop making sense. The reason for this might be more profound than we initially thought. Gravity doesn't seem to behave like a typical force at all. Instead, it acts more like the very fabric of reality itself, like the shape of the universe. But here's where things get really strange. If gravity is just geometry, how can it follow quantum rules? How can the shape of space itself become uncertain or probabilistic? Think about what a particle actually is in our modern understanding. We used to imagine tiny little spheres bouncing around, but that picture has completely changed. Particles are more like waves in invisible fields that fill all of space. An electron is really just a ripple in something we call the electron field. Light is a ripple in the electromagnetic field. These ripples can appear, disappear, and even interfere with each other in ways that seem almost magical. This brings us to a fascinating question. If everything else is made of field ripples, what about gravity? If there's a gravitational field, what would its ripples look like? We've actually detected these ripples. They're called gravitational waves, but they behave very differently from other quantum fluctuations. They're incredibly gentle and weak, almost like whispers compared to the violent quantum chaos we see everywhere else. The way we measure things in these two theories creates another deep contradiction. In the smooth world of relativity, measurement is straightforward. You point an instrument at something, take a reading, and that's that. But quantum mechanics tells us something much stranger. The very act of measurement actually changes what you're measuring. Before you look at a quantum system, it exists in what we call a superposition. It's in all possible states at once. But the moment you observe it, something mysterious happens. The wave function collapses, and the system suddenly behaves like a normal, everyday object. Nobody really understands why this happens or what triggers it. Some scientists think collapse is a real physical process. Others believe it's just an update in our information about the system. There's even a theory that suggests collapse never happens at all, that all possible outcomes continue to exist in parallel universes. But none of these ideas fit well with our understanding of space and time. Motion itself becomes puzzling when we try to combine these theories. In the smooth world, objects follow clear paths through space and time, but in the quantum world, particles don't travel from one point to another on a single route. Instead, they somehow take every possible path simultaneously. The probabilities from all these paths interfere with each other to produce what we actually observe. This creates a mind-bending question. If a particle samples every possible path, does it also experience every possible curvature of space along the way? Does the shape of space influence these quantum probabilities? Or do the probabilities somehow shape space itself? These questions sit right at the heart of our confusion about reality. Even empty space behaves differently in these two pictures. According to relativity, empty space is truly empty, a neutral stage where events unfold. But quantum mechanics paints a very different picture. Empty space is never actually empty. It's constantly bubbling with temporary particles that pop into existence and vanish again almost instantly. If space and time fully followed quantum rules, this constant bubbling should dramatically affect the curvature of space. The universe should be wildly turbulent, but it isn't. Something keeps these quantum fluctuations from completely dominating the smooth geometry we observe. This represents one of the biggest mismatches between theory and reality in all of physics. The role of the observer creates yet another puzzle. In relativity, objects have definite properties whether anyone is looking at them or not. A mountain has a specific height. A planet follows a particular orbit, regardless of who might be watching. But quantum mechanics suggests something radically different. Properties don't exist until someone measures them. The act of observation literally creates the reality we observe. This introduces a subjective element that makes many physicists uncomfortable. Relativity insists that the laws of physics must be the same for everyone, everywhere, but quantum mechanics seems to give observers a special role in determining outcomes. These perspectives appear fundamentally incompatible. Perhaps most unsettling is how quantum mechanics, despite all its strangeness, makes incredibly accurate predictions. It describes the behavior of atoms, molecules, and subatomic particles with stunning precision. Every test we perform confirms its predictions. Yet it feels like it belongs to a completely different universe from the one described by relativity. This tension between two successful but incompatible theories drives much of modern physics research. Scientists are searching for a deeper understanding, a more fundamental theory that might explain why reality appears to have these two completely different faces. They're looking for something that can explain why the quantum world seems so chaotic and uncertain, while space and time appear so smooth and predictable. The search continues, driven by the hope that somewhere beneath these contradictions lies a more complete picture of reality, a picture that might finally explain why our universe seems to follow two completely different sets of rules, depending on how closely we look. Gravity sits in this strange position, where it's both the most familiar thing we experience and one of the most puzzling mysteries in all of science. You encounter it constantly, every single day, yet it behaves in ways that don't quite fit with everything else we know about how the universe works. What's remarkable is just how weak gravity actually is compared to other forces in nature. Think about this for a moment. A tiny refrigerator magnet can pull a paperclip upward, completely overpowering the gravitational pull of our entire planet. That small magnetic force defeats the combined gravity of 6 trillion kilograms of rock and metal beneath your feet. The electromagnetic force from that little magnet is stronger than the gravitational force from the whole Earth. This creates a fascinating puzzle. If gravity is so incredibly weak, why does it end up controlling the large-scale structure of the universe? Why do planets orbit stars? Why do stars cluster into galaxies? Why does the cosmic web stretch across billions of light years, all held together by this gentle, almost whisper-quiet force? The answer lies in something unique about gravity. Unlike other forces, gravity never repels. It never cancels itself out. Every bit of mass in the universe adds to the total gravitational pull. There's no such thing as negative mass to counteract positive mass. Electromagnetic forces can neutralize each other when positive and negative charges meet. But gravity just keeps accumulating, building up, becoming stronger as more matter gathers together. Even stranger is how gravity treats everything exactly the same way. It doesn't matter if something is made of iron or feathers, if it's electrically charged or completely neutral, if it's hot or cold. Gravity pulls on everything with mass or energy in precisely the same way. This universality is almost unsettling when you think about it. Other forces are picky. Electromagnetism only affects charged particles. The strong nuclear force only works inside atomic nuclei. But gravity reaches out to touch absolutely everything. This universal nature of gravity led Einstein to a radical idea. Maybe gravity isn't really a force at all. Maybe it's something built into the fabric of space and time itself. Maybe massive objects don't pull on other objects. Maybe they bend and warp the geometry of space-time, and other objects simply follow the curved paths that this warped geometry creates. Einstein's vision worked beautifully for explaining many things we observe. It predicted how light bends around massive stars during solar eclipses. It explained the precise orbit of Mercury around the Sun. It described how time runs slower in stronger gravitational fields. But it also opened up new questions that we still can't answer today. If gravity is the curvature of space-time, what exactly is doing the curving? What does it even mean for space and time to bend? The mathematics describes the relationship between matter and curvature with incredible precision, but it doesn't reveal the underlying mechanism. It's like having a perfect recipe that always produces the right result, but never knowing what the ingredients actually are. This mystery becomes even deeper when we look at black holes. These objects form when matter collapses under its own gravity, so completely that nothing can escape, not even light itself. Einstein's equations describe the space around black holes perfectly. They predict how objects fall in, how light bends nearby, how time slows down as you approach the edge. All of this matches what astronomers observe, but something strange happens when you try to use the same equations to describe what's happening at the very center of a black hole. The mathematics breaks down completely. Quantities that should stay finite suddenly become infinite. The curvature of space-time becomes mathematically undefined. This breakdown isn't telling us that the universe itself falls apart. At that point, it's telling us that our understanding reaches a hard limit. The same kind of mystery shows up when we look at galaxies. When astronomers measured how fast the outer edges of galaxies rotate, they found something unexpected. The edges were spinning much faster than they should have been, based on the amount of visible matter in those galaxies. There wasn't enough gravitational pull from stars and gas to keep those outer regions moving so quickly. The most straightforward explanation was the galaxies must contain much more mass than we can see, something invisible but massive enough to provide the extra gravitational pull. This invisible mass became known as dark matter, but decades of searching haven't revealed what dark matter actually is. It doesn't emit light, it doesn't interact with electromagnetic fields, it doesn't show up in particle detectors. Yet, its gravitational effects shape the structure of every galaxy in the universe. Gravity is acting like a messenger here, showing us the effects of something we can't directly detect. It's pointing to the presence of matter we can't see, energy we can't measure, phenomena we don't understand. The gravitational clues are clear and consistent, but the source remains hidden. An even stranger mystery emerged when astronomers discovered that the expansion of the universe is actually speeding up. Something is pushing space itself apart, causing galaxies to move away from each other at an accelerating rate. This force has been named dark energy, but no one knows what it is or where it comes from. Once again, gravity is the messenger, showing us that space-time is stretching faster than it should, but not revealing why. These puzzles become even more challenging when physicists try to connect gravity with quantum mechanics. Quantum mechanics describes the behavior of particles and energy at the smallest scales with extraordinary accuracy. Gravity describes the behavior of space-time at the largest scales equally well. Both theories are cornerstones of modern physics, but they refuse to work together. In quantum mechanics, forces are carried by particles. The electromagnetic force is carried by photons. The weak nuclear force is carried by W and Z bosons. The strong nuclear force is carried by gluons. But when physicists try to treat gravity as a force carried by particles called gravitons, the mathematics explodes into infinities that can't be resolved. Meanwhile, Einstein's view treats gravity not as a force carried by particles, but as the geometry of spacetime itself. But trying to apply quantum rules to geometry leads to contradictions with the existing framework of quantum field theory. Each approach works beautifully on its own, but they create conflicts when brought together. This creates one of the deepest tensions in all of physics. If gravity is geometry, then quantum particles must exist within that geometry. But if spacetime itself becomes uncertain and probabilistic at the smallest scales, then the geometry must also follow quantum rules. This means gravity should be quantized too, but every attempt to quantize gravity leads to mathematical inconsistencies that don't arise with other forces. Part of the difficulty comes from gravity's unique properties. Other forces can be shielded or cancelled out. You can create regions where electromagnetic forces are neutralized. The strong nuclear force is naturally confined to tiny regions inside atomic nuclei, but gravity extends everywhere. It cannot be blocked or turned off. You can't create a laboratory where gravity is absent. You can't isolate an experiment from gravitational influence the way you can shield it from other forces. This makes gravity extremely difficult to study under controlled conditions. The quantum effects of gravity only become significant at incredibly high energies or in extremely dense regions. These are precisely the conditions we cannot recreate in laboratories. The universe provides few natural laboratories where gravity and quantum mechanics collide, and most of them, like the centers of black holes, are hidden from direct observation. Another subtle problem is that gravity defines the stage on which all physics happens. Quantum mechanics assumes a fixed background, a stable framework that doesn't change during an experiment. But gravity refuses to provide such a stage. It curves space and time. It changes distances and timing. It shapes the very framework within which other physical processes occur. This creates a circular problem. Quantum mechanics needs a fixed spacetime to function properly. Gravity insists that spacetime is never truly fixed. Even simple questions become tangled. What happens at the exact point where a quantum particle interacts gravitationally with spacetime? Does the particle create ripples in the geometry? Do these ripples have quantum properties? Is space-time itself smooth or grainy at the smallest scales? These aren't signs that physics is broken or failing. They're signs that we haven't reached the complete picture yet. They show us the boundaries of our current understanding. And gravity is one of the main places where these boundaries become obvious. What makes this even more profound is that gravity doesn't behave mysteriously out of stubbornness. It behaves differently because it's fundamentally connected to the shape and structure of reality itself. Everything that happens in the cosmos depends on the geometry that gravity creates. The formation of stars and planets, the clustering of galaxies, the bending of light, the flow of time, the expansion of space itself. In a sense, gravity is the universe's way of telling its own story. It shapes the stage, writes the script, and directs the performance all at once. Yet, despite its central role in everything we observe, it remains the least understood of all the fundamental forces. Perhaps that's fitting for something so deeply woven into the fabric of existence. The more central something is to reality, the more mysterious it becomes when we try to understand what it really is. Looking at the universe feels a bit like standing at the edge of a vast puzzle, where two enormous pieces simply refuse to fit together. We have these two magnificent ways of understanding reality, and each one works beautifully on its own. But when you try to bring them together, they start arguing like stubborn relatives at a dinner table. The big picture shows us a cosmos where everything flows smoothly. Galaxies drift through space following gentle curves, stars burn steadily for billions of years, and planets trace predictable orbits around their suns. Einstein showed us that massive objects actually bend the fabric of space and time itself, creating these graceful paths that everything follows. It's a universe where you can zoom in endlessly, finding smooth curves and gradual changes everywhere you look. But then there's this other world, the tiny world, where absolutely nothing sits still. Down at the smallest scales, particles refuse to behave themselves. They flicker in and out of existence. They exist in multiple places at once. They tunnel through walls that should be impossible to cross. Nothing has a definite position. Nothing follows a clear path. And everything exists as a cloud of possibilities that only becomes real when you actually look at it. Each world has its own personality, you might say. The large-scale universe believes in certainty and smooth transitions. The small-scale universe thrives on uncertainty and sudden jumps. And here's the strange thing. Reality insists on using both sets of rules at the same time, even though they contradict each other completely. Think about what happens when you try to describe a single particle moving through curved space. The big picture says the particle should follow a smooth, curved path determined by the geometry around it. But the small picture says that particle doesn't even have a definite path. It's smeared out across many possible routes simultaneously. You end up trying to force two completely different languages to describe the same event, and neither one wants to cooperate. Energy creates another fascinating conflict. In the big picture, energy curves space and time in very predictable ways. More energy means more curvature, and the relationship follows clear mathematical rules. But in the tiny world, energy fluctuates wildly, even in completely empty space. These fluctuations happen so fast and so frequently that if the big picture rules applied to them, they would twist space and time into impossible knots. Yet somehow, empty space remains relatively calm and stable. The mismatch becomes even more dramatic when you shrink your viewpoint down to incredibly small scales. If you could somehow look at a region millions of times smaller than an atom, the smooth geometry that the big picture relies on starts to break apart. Distances become uncertain, time becomes blurry, and even the basic shape of space itself starts fluctuating randomly. But the big picture equations need precise geometry to function properly. It's like trying to draw a perfect circle while riding on a bucking horse. The foundation keeps shifting beneath you. Scientists have tried to describe gravity using the same approach that works for other forces. Electromagnetic forces are carried by particles called photons, and the strong nuclear force uses particles called gluons. Following this pattern, gravity should be carried by particles too, theoretical particles called gravitons. But when physicists try to build equations using gravitons, the mathematics explodes into nonsense. The calculations produce infinite answers that can't be removed or ignored, suggesting that gravity simply doesn't want to be treated like other quantum forces. This fundamental disagreement reveals something profound about the nature of reality. The large-scale universe operates through geometry, through the bending and stretching of space and time itself. The small-scale universe operates through probability, through clouds of possibility that collapse into definite outcomes only when observed. These two approaches seem to come from completely different philosophical traditions about how reality should work. The conflict becomes especially obvious when we try to understand the very beginning of everything. If you follow the expansion of the universe backward in time, you eventually reach a point where everything was compressed into an incredibly tiny, incredibly dense region. That region was small enough that quantum rules should definitely apply, but dense enough that gravitational effects should dominate everything. Both sets of rules should be essential for understanding what happened there. But when you apply big-picture physics to that moment, you get a mathematical singularity, a point where density becomes infinite and the equations simply break down. When you apply small-picture physics, the mathematics refuses to accept infinite values as meaningful answers. The two approaches argue so violently with each other that neither can provide a clear description of the most important moment in cosmic history. Black holes create a similar standoff. The outer regions around a black hole can be described beautifully using gravitational physics. The curvature is intense, but manageable, and you can predict how objects will behave as they approach. But as you get closer to the center, the density becomes enormous and quantum effects should take over. Yet gravitational physics continues predicting infinite curvature at the center, while quantum physics insists that infinities can't represent anything physically real. Even the basic treatment of space and time creates conflicts between these two worldviews. In the big picture, space and time are woven together into a flexible fabric that stretches and bends based on motion and gravity. But quantum equations assume that space and time form a stable, unchanging background stage where particles can dance around. The particles and fields change constantly, but the stage itself remains steady and reliable. This assumption is absolutely essential for quantum calculations to work properly, but it directly contradicts everything we know about relativity. The big picture insists that the stage is never steady. It curves and shifts constantly in response to everything happening on it. Trying to apply quantum rules to a constantly shifting stage leads to equations that refuse to behave sensibly. The more precisely you try to measure tiny distances, the more energy you need to do the measurement. But high energy creates curvature in space and time, which distorts the very thing you're trying to measure. If you push this process far enough, the energy required for the measurement becomes so large that it creates a tiny black hole right where you're trying to look. The black hole then hides the region from view completely, making the measurement impossible. In other words, the universe seems to have built in a fundamental limit to how closely we can examine its smallest scale structure. Information creates another puzzle. Quantum physics has a strict rule that information about the state of any system must be preserved over time. The information might get scrambled or spread out in complicated ways, but it can never simply disappear. But black holes seem to destroy information permanently. If something falls into a black hole, all the information describing that object appears to vanish from the universe forever. This creates what physicists call the information paradox, and despite decades of effort, no solution has been universally accepted. Particles themselves behave in ways that the two worldviews can't reconcile. Quantum particles can tunnel through barriers that should be impossible to cross. They can exist in superpositions, where they're in multiple states simultaneously, and they don't settle into definite states until something measures them. But gravitational physics describes particles moving along definite paths shaped by the geometry of curved space and time. There's no room in that framework for superpositions of paths, or for tunneling through barriers created by smooth continuous curvature. Even the basic concept of space breaks down differently in each theory. The big picture treats space as part of a four-dimensional geometric structure, where curvature is built into the fabric itself. The small picture treats space as an arena where quantum fields operate. but it doesn't have inherent curvature unless gravity somehow enters the equations. And when gravity does enter quantum descriptions, the mathematics often becomes unstable and unpredictable. End quote. Time doesn't fare much better. In gravitational physics, time depends on motion and gravity. It runs slower in strong gravitational fields and for objects moving at high speeds. But in quantum physics, time is treated as a universal parameter that ticks along uniformly everywhere. This fundamental mismatch in how time is handled represents one of the deepest obstacles preventing these two worldviews from working together. Perhaps the most dramatic failure involves something called vacuum energy. Quantum mechanics predicts that empty space should be filled with enormous amounts of energy from particles constantly popping in and out of existence. Gravitational physics predicts that this energy should curve space and time dramatically, but when we look at actual empty space, the curvature is incredibly tiny, almost zero. The two predictions differ by a factor so enormous that many physicists consider it the biggest quantitative failure in the history of theoretical physics. Quantum entanglement creates yet another subtle conflict. When two particles become entangled, measuring one instantly affects the state of the other, no matter how far apart they are. This doesn't violate relativity's speed limit because no information actually travels between the particles, but it does create correlations that appear to be instantaneous across vast distances. This challenges the strict causal structure that gravitational physics relies on, suggesting that perhaps space and time aren't the full story. All of these conflicts and contradictions point toward a rather unsettling conclusion. The universe doesn't present us with a unified, consistent picture when we study it through these two magnificent but incompatible frameworks. Each approach reveals important truths about reality, but neither one seems to have room for the other's insights. It's as if we're looking at two partial reflections of some deeper truth that neither framework can capture completely on its own. The large scale ignores the small scale's insistence on uncertainty and probability. The small scale ignores the large scale's geometric elegance and smooth curvature. They operate according to completely different philosophical principles about how reality should be structured, and each one works beautifully within its own domain. But the universe itself operates in a realm where both sets of rules should apply simultaneously, creating a tension that has puzzled scientists for nearly a century. Perhaps this tension is telling us something profound about the nature of knowledge itself. Maybe reality is simply too rich and complex to be captured by any single theoretical framework, no matter how elegant or powerful. Or maybe we're still missing some crucial insight that would allow these two worldviews to finally work together harmoniously, revealing an even deeper layer of cosmic structure that we haven't yet learned to perceive. The act of measuring anything in our universe carries a peculiar burden that most people never consider. Every time scientists attempt to gauge distance, time, or any fundamental property, they're working within a framework that refuses to hold still. Space itself stretches and contracts. Time speeds up and slows down depending on where you happen to be standing. The very tools we use to measure these phenomena get influenced by the same forces they're trying to detect. Picture yourself trying to measure a room while someone continuously rearranges the furniture around you. Each individual measurement seems reasonable, but when you compare different readings, the inconsistencies become impossible to ignore. This captures something essential about how measurement works in our cosmos. We often imagine scientific work happening against a stable backdrop, with rulers staying the same length, clocks ticking at steady rates, and everything maintaining its proper place. Reality operates quite differently. The foundation we stand on constantly shifts beneath our feet. This creates layers of complexity that make even simple measurements surprisingly intricate. When you send a beam of light from one location to another, the path it travels depends on how space curves along the way. When you measure time with the most precise clock available, the rate it ticks depends on the gravitational environment where you place it. You can never step outside the system to observe it from some neutral position. Every observation happens from within, subject to the same forces that shape what you're trying to measure. Scientists discovered this unsettling truth through experiments designed to detect something called the ether. Researchers once believed this invisible substance filled all of space, providing a medium for light waves to travel through. If Earth moved through this cosmic ocean, instruments should detect differences in light speed depending on which direction you pointed your measuring device. But no matter how carefully they looked, no difference appeared. Light traveled at exactly the same speed in every direction. This result revealed something profound about the structure of reality itself. The universe adjusts its geometry to keep light speed constant for every observer, regardless of how they move. Space and time bend and flex to maintain this fundamental relationship. Once Einstein recognized this principle, the entire concept of measurement had to be reconsidered. Distances couldn't be assumed identical for different observers. Clocks wouldn't tick at universal rates. Even basic definitions of length and time became dependent on motion and gravitational conditions. These aren't merely theoretical curiosities. GPS satellites carry extremely precise timepieces that tick at different rates than identical clocks on Earth's surface. The difference stems from gravitational effects that alter how time flows at different altitudes. Without correcting for these variations, your navigation would drift dramatically. Our everyday technology must account for the fact that space-time moves unevenly throughout its structure. The challenges become even more intricate when you consider curved space-time. In perfectly flat geometry, you can stretch a measuring tape between 2 points and expect consistent results, regardless of where you perform the measurement. But in curved space, different paths between the same 2 points yield different distances. The curvature itself depends on the distribution of mass and energy, which means the environment continuously reshapes the stage you're trying to map. Attempting to measure space-time at incredibly tiny scales introduces quantum effects that make the stage even more unstable. Precise measurements require high energy. That high energy distorts the very space-time you're examining. At large scales, these distortions remain negligible. At microscopic scales, they become overwhelming. Push the measurement precision too far, and the energy involved risks creating tiny black holes that destroy the measurement entirely. The universe seems to guard its smallest secrets behind this fundamental barrier. This problem sits precisely where relativity meets quantum mechanics. Relativity treats spacetime as smooth and continuous. Quantum mechanics insists that uncertainty dominates small scales. When these frameworks collide, spacetime flickers and shifts in ways that neither theory can fully describe. The stage becomes something that resists complete measurement by either approach. Cosmological measurements present their own unique difficulties. The universe expands continuously, causing distances between galaxies to grow over time. If you attempt to measure the universe's size, your result depends on when you make the measurement, how fast expansion is occurring, and which geometric model you apply. You're measuring something that changes while you're measuring it. The light from distant objects takes billions of years to reach us, during which time the space between us and those objects has stretched considerably. This expansion creates a fundamental question about what distance even means on cosmic scales. Are you measuring the distance light traveled when it started its journey? The distance it travels through expanding space, or the distance that exists when the light finally arrives? Each interpretation gives different answers, and all of them contain valid aspects of the truth. Gravitational waves add another layer of complexity to precision measurements. These ripples in space-time stretch and compress space as they propagate outward from their sources. When observatories detect these waves, they use laser beams to measure minuscule changes in distance between carefully positioned mirrors. But the waves don't simply move the mirrors, they alter the space between them. The entire measuring apparatus shifts along with the phenomenon being measured. The remarkable thing about gravitational wave detection is that meaningful data can still be extracted despite this fundamental entanglement. The stretching and compression follow specific patterns that reveal information about the cosmic events that created them. Even so, the process demonstrates how unstable spacetime becomes when dramatic events occur elsewhere in the universe. Consider what happens when you try to measure distances during cosmic expansion. If you place two reference points far apart, the space between them grows not because the points move through space, but because space itself stretches. This stretching occurs everywhere simultaneously, affecting every measurement tool and reference frame. You cannot find a stable platform from which to observe this expansion, because every platform participates in it. The absence of any absolute reference frame represents perhaps the most philosophically challenging aspect of modern measurement. There exists no special location where time ticks normally, no neutral background where everything behaves predictably, no universal stage that remains fixed while events unfold upon it. Every position, every speed, every gravitational environment creates its own version of time and space. Each version remains perfectly valid from its own perspective. This relativity of measurement forces scientists to specify their reference frame for every observation. Without clearly stating the conditions under which a measurement was made, the result becomes meaningless. Two observers moving at different speeds will measure different distances between the same two objects. Both measurements are correct within their respective frames. Neither has priority over the other. The philosophical implications extend far beyond physics. If even the most fundamental aspects of reality, space and time themselves, depend on perspective, what does this suggest about the nature of truth? Perhaps absolute truth, at least regarding physical measurements, simply doesn't exist. Perhaps reality consists of a vast collection of equally valid perspectives, each capturing part of a deeper truth that transcends any single viewpoint. These measurement challenges reveal something beautiful about the universe's structure. Rather than being rigid and mechanical, space-time displays remarkable flexibility. It adjusts itself to maintain certain relationships, like the constancy of light's speed, while allowing other properties to vary. This flexibility enables the rich variety of phenomena we observe, from the precise orbits of planets to the spectacular collisions of black holes that send gravitational waves rippling across cosmic distances. The universe seems designed to prevent any single observer from claiming a privileged perspective. Every measurement tool becomes subject to the same forces it attempts to measure. Every observer remains embedded within the system they're trying to understand. This creates a kind of cosmic humility, a recognition that complete knowledge might be fundamentally impossible, not due to limitations in our instruments or theories, but because of the very structure of reality itself. Perhaps this represents the universe's greatest teaching, that understanding comes not from standing apart and observing, but from recognizing our intimate participation in the phenomena we seek to comprehend. The stage doesn't simply hold still for our measurements, because we are part of the performance, part of the ongoing cosmic dance of space and time. The idea of measuring something while that something is constantly changing creates a puzzle that goes far beyond simple mathematics. When 2 points in space are moving apart from each other, how fast they separate depends entirely on how you choose to measure that separation. Your choice of coordinates becomes crucial. In some systems of measurement, those points might seem to fly apart, faster than light itself can travel. In other systems, they move at perfectly ordinary speeds. The velocity stops being a real physical thing and becomes more like a definition, a choice you make about how to describe what you see. This flexibility reveals something unsettling about measurement when the entire framework is shifting beneath your feet. Space doesn't stay still long enough for you to get a clean reading. Even something as basic as a straight line becomes difficult to pin down. In curved spacetime, what we call a straight line is really just the path that covers the shortest distance between 2 points. But since distances themselves depend on how curved the space is, those paths bend and twist, even though they count as straight within that particular geometry. These special paths have a name, geodesics, and they represent the routes that objects naturally follow when nothing else pushes or pulls them. But here's where things get circular, in an almost philosophical way. To measure these paths properly, you need to know how curved the space is, but to figure out the curvature, you need to measure the paths. Each step requires the other. Measurement and theory become tangled together in a loop where neither can exist without the other. The tools we use to measure things make this even more complicated. Physical rulers stretch and contract depending on where you place them. Clocks tick faster or slower based on how deep they sit in a gravitational field. The very instruments we design to give us precise measurements become subject to the same effects they're trying to detect. It's like trying to measure a moving river with a measuring stick that gets carried along by the current. If you put a clock close to a massive object, it will tick more slowly than an identical clock placed farther away. But the slow clock can't tell you it's running slow. From its own perspective, it behaves perfectly normally. Only when you compare it to the other clock does the difference show up. This means measurement often requires comparing different regions of spacetime, and those comparisons can't be made without taking the geometry itself into account. Motion adds another layer of complexity because motion is always relative to something else. If you try to measure spacetime while moving through it, your rulers contract and your clocks slow down. If you try to measure it while standing perfectly still, your stillness is just a matter of perspective. Someone else might see you moving at high speed. You can only measure from your own reference frame, and your frame might not reveal the deeper structure of what you're measuring. This makes the interpretation of results just as important as the measurement itself. These challenges become even more severe when we consider theories that go beyond relativity. Some proposed ideas suggest that space-time itself might be emergent, arising from deeper structures that don't resemble geometry at all. If space-time isn't fundamental, but instead forms from something more basic, then measuring it becomes even stranger. You'd be measuring something that emerges from something else entirely, like trying to measure how smooth water is while ignoring the molecules that create that smoothness. Every measurement would give you a large-scale view without revealing the microscopic details that matter most. All of these difficulties point toward a larger question that touches on how we understand reality itself. If spacetime is always moving, always changing, always dependent on your perspective, how can anyone claim to understand it completely? The answer might be that true understanding doesn't come from trying to freeze spacetime into a fixed shape. Instead, it comes from learning how the movement works, accepting that measurement in spacetime is never simple, never detached, never independent of the thing being measured. Every observation becomes part of the structure you're trying to understand. Every measurement sits within the geometry it's attempting to map. This creates a kind of participatory universe where the act of looking changes what you see, not because of any mystical influence, but because of the fundamental nature of spacetime itself. Geometry, when you first encounter it, seems like one of the most stable concepts humans ever developed. It brings to mind straight lines that never waver, perfect circles that maintain their shape, triangles whose angles always add up to the same total. These shapes feel permanent, unchanging, reliable in a way that few other ideas can match. When you learned geometry in school, it probably felt like a calm, predictable subject that had figured itself out long ago and never changed its mind about anything. But the universe treats geometry very differently than textbooks do. Once you add gravity into the picture, along with motion, energy, and the flexibility of spacetime, geometry stops being a quiet collection of fixed shapes. Instead, it becomes something dynamic, responsive, adaptive. It warps and stretches and rearranges itself whenever something enters its environment. It acts less like a rigid set of rules and more like a living system that constantly adjusts to whatever happens around it. This behavior isn't intuitive because our everyday experiences don't reveal it directly. You don't feel the floor bending under your feet as you walk across a room. You don't see walls curving when someone passes by. You don't sense time changing its pace depending on where you stand. Everything nearby feels stable, and that stability encourages the belief that geometry itself is fixed and permanent. So the idea that the shape of space can change strikes most people as strange, even impossible. Yet, this is exactly what Einstein demonstrated. What he described wasn't just a mathematical trick or an abstract concept. It represented a fundamental shift in how the universe handles structure itself. One way to get a feel for this is to imagine placing a heavy ball on a stretched rubber sheet. The sheet bends downward around the ball, and anything rolling across it changes direction because of that bending. The rolling objects aren't being pulled by some invisible force. They're simply following the shape of the surface beneath them. This analogy gets used often to illustrate how spacetime curves, and while it isn't perfect, it does capture something important about how geometry reacts and adjusts itself to whatever is present. The real universe takes this idea much further, though. because space-time doesn't bend into some larger space the way the rubber sheet bends downward in the demonstration. Space-time bends within itself. It's not a surface resting on something bigger. It is the entire structure in which everything exists. When that structure changes shape, nothing can escape its influence because there's nowhere else to go. There's no outside to exit into. Once you accept that geometry can change, the next surprise is discovering how much it can change. Add mass to a region of space, and the geometry bends inward around it. Remove mass, and it flattens out. Let the universe expand, and the geometry stretches along with it. Bring gravity to intense levels near a compact object, and the bending becomes dramatic. When two massive objects orbit each other, the curvature they create interacts and sends ripples traveling outward at the speed of light. Suddenly, geometry stops looking like a collection of static diagrams and starts resembling something that responds with a kind of fluidity, the way water changes shape around whatever moves through it. These changes aren't optional or accidental. They're required by the fundamental laws of physics. When an object moves, it influences the geometry around it. When energy flows from one place to another, the geometry shifts accordingly. When pressure builds up inside a star, the geometry adjusts to accommodate that pressure. Even empty space that contains no matter or energy that we can detect, has geometry built into it. So geometry becomes something that evolves moment by moment, something that never stays frozen in time. You can think of it as a constantly updated record of everything happening in the universe, shaped by the presence and motion of matter and energy. It's particularly striking how sensitive space-time is to the presence of mass. Earth curves space-time just enough to keep the moon orbiting around it. The sun curves space-time sufficiently to hold all the planets in their smooth, predictable paths. Massive stars curve space-time so strongly that light itself bends as it passes nearby. Black holes curve it so deeply that the geometry closes in on itself, creating regions where the normal rules of measurement break down entirely. Each of these examples shows that geometry isn't a passive backdrop for events. It reacts to what surrounds it, actively shaping how everything within it moves and behaves. The way planets orbit isn't just about forces pulling and pushing. It's the result of geometry itself telling objects how to move through space-time. Geometry in our universe acts more like a living entity than the rigid shapes we learned about in school. When you place mass anywhere in space, the fabric of reality responds right at that spot, creating curves and bends in what we call space-time. Think of it as dropping a heavy ball onto a stretched rubber sheet. The surface dips immediately where the ball sits. This immediate response doesn't violate the speed of light limit though. What travels outward at light speed are the changes, the adjustments that ripple through space like waves on water. These ripples are gravitational waves, and they tell us something profound about the nature of reality itself. When massive objects like black holes spiral into each other, they don't just create disturbances in space. They make space-time itself vibrate, like striking a cosmic drum that rings throughout the universe. The entire fabric of reality stretches and compresses in rhythmic patterns as these waves pass by. Scientists have actually detected these vibrations, confirming that the geometry around us isn't silent or still. It moves, it oscillates, it carries information about the events that created it. Every gravitational wave that reaches Earth tells a story about colliding neutron stars or merging black holes that happened millions of years ago. The stretching we can measure is incredibly tiny, smaller than a fraction of a proton's width, but the fact that we can measure geometry itself vibrating reveals something remarkable about the universe we live in. Space and time aren't just a stage where physics happens, they're active participants in the cosmic drama. This becomes even more striking when you consider how the entire universe has been expanding since the Big Bang. Galaxies aren't flying away from each other through empty space. Instead, the space between them is growing. New distance is being created constantly, stretching the fabric of reality itself. This expansion isn't happening into some pre-existing void either. There's no outside container that the universe is growing into. The very concept of distance, of here and there, is what's increasing. It's as if the universe is writing its own rules for size and separation as it goes along. When you really think about it, this makes measurement itself a philosophical puzzle. Every time you measure something, you're using a geometry that responds to your very presence. The light you use to see travels along paths that are shaped by the mass of everything around, including yourself. Near extremely dense objects like neutron stars, this responsive geometry creates effects that seem almost magical. Time itself slows down, not because clocks malfunction, but because the flow of time is part of the geometric structure that's being warped. A clock sitting near a neutron star runs perfectly from its own perspective, but compared to a clock far away, it's moving through time at a different rate. This isn't a mechanical problem, it's geometry controlling the pace of existence itself. Every type of clock, whether digital, mechanical, or atomic, slows down by exactly the same amount. This universal effect happens because gravity isn't really a force pulling on objects. It's the curvature of space-time affecting the flow of time and the meaning of straight lines. This challenges our usual way of thinking about natural laws. We often imagine physics as fixed rules operating on a stable stage, but here the stage itself is dynamic. Add more mass to a region and the geometry curves more dramatically. Remove mass and it flattens out. The rules for how things move stay consistent, but the results look completely different because the playing field keeps changing. It's like trying to play a game where the board reshapes itself based on where you place your pieces. Geometry can even store and transmit information, acting more like a recording medium than a passive backdrop. When two massive objects orbit each other for millions of years, they leave their signature in the surrounding curvature. When they finally merge, the resulting gravitational waves carry detailed information about their masses, spins, and orbital patterns. These waves don't just announce that something happened somewhere in the universe, they provide a complete data package about the event. Scientists can decode the shape of these ripples to reconstruct the entire collision, learning about objects they could never observe directly. This information-carrying capacity suggests that geometry behaves more like a participant than a background. It's actively involved in cosmic events, recording their details and broadcasting them across space and time. Energy in any form can curve space-time, not just mass. Light bends geometry, radiation curves it. Even pressure creates curvature. This means the fabric of reality is constantly listening to everything that carries energy, responding to the full spectrum of physical phenomena. In the early universe, when radiation dominated over matter, these energy-induced curves played a crucial role in shaping cosmic evolution. The geometry wasn't just responding to clumps of matter, it was reacting to intense energy fields that filled all of space. Some scientists wonder whether spacetime itself might be built from something even more fundamental, emerging from deeper interactions we haven't discovered yet. If geometry arises from countless microscopic processes working together, then its dynamic behavior would make perfect sense. Think of how temperature emerges from the motion of individual particles. No single atom has temperature, but collectively they create this property we can measure and feel. Geometry might work similarly, with no fundamental building blocks having curvature, but their collective behavior creating the responsive spacetime we observe. This possibility transforms our understanding of reality's foundation. Instead of geometry being a fixed arena where physics plays out, it becomes an ongoing result of deeper processes, always adjusting to new conditions, always in motion. The concept has drifted far from simple mathematical shapes into something that resembles a living system. Modern geometry breathes with the universe, recording its history while continuously adapting to its changing contents, creating a dynamic partnership between matter, energy, space, and time. When we think about the far reaches of our universe, there's something profoundly unsettling about the silence that surrounds certain objects. It's not the absence of sound, but rather the presence of mysteries so deep, they seem to swallow our questions whole. Black holes represent one of those cosmic enigmas, sitting at the intersection of everything we know and everything we're still trying to figure out. Picture a star, maybe 20 or 30 times more massive than our Sun, reaching the end of its life. The nuclear fires that kept it burning for millions of years finally die out, and gravity takes over completely. The collapse happens fast, really fast, crushing matter into densities that boggle the mind. What emerges from this cosmic catastrophe is something that defies our everyday understanding of reality. The mathematics we use to describe these objects work beautifully, up to a point. Einstein's equations can tell us about the gravitational pull, the way matter spirals inward, heating up until it glows brighter than entire galaxies. But then something strange happens. The closer our calculations get to the center, the more the numbers start misbehaving. They climb toward infinity, which in physics usually means we're missing something important. This breakdown isn't just a mathematical curiosity. It's telling us that our theories, as elegant as they are, have limits. Somewhere in the heart of a black hole, space and time curve so severely that our usual rules simply stop working. We call this breakdown a singularity, but that's really just a fancy way of admitting we don't know what's actually happening. Here's where things get philosophically interesting. We're dealing with objects that exist in our universe, objects we can observe and measure, yet their cause remain fundamentally unknowable with our current understanding. It's like having a book where the final chapter is written in a language that doesn't exist yet. The problems multiply when we try to bring quantum mechanics into the picture. While Einstein's relativity describes gravity as the curvature of spacetime, quantum mechanics operates on completely different principles. These two frameworks, both incredibly successful in their own domains, start arguing when black holes enter the conversation. Quantum mechanics has this fundamental rule: information can never be truly destroyed. It might get scrambled, scattered, or hidden in ways that make it nearly impossible to retrieve, but it's always there somewhere. Black holes seem to violate this principle completely. When something falls past the event horizon, that invisible boundary where escape becomes impossible, all the information about that object appears to vanish from the universe forever. Imagine dropping your diary into a black hole. According to relativity, once it crosses that boundary, every word, every thought you wrote down, is lost to the universe permanently. But quantum mechanics insists that's impossible. The information must go somewhere, must be preserved somehow. This disagreement has puzzled physicists for decades, creating what we call the information paradox. The event horizon itself presents another puzzle. It's not a physical surface like the edge of a planet. There's nothing there you could touch or bounce a ball off. Instead, it's a geometric boundary, defined purely by the extreme curvature of spacetime. From the outside, it marks the point of no return. But for someone falling in, there's nothing special about crossing it. They wouldn't even notice the moment they pass the boundary. This creates one of the most mind-bending aspects of black holes. Two observers, one falling in and one watching from a safe distance, experience completely different realities. The outside observer sees the falling person slow down, freeze at the horizon, their image growing dimmer and redder until it fades away. But the falling observer experiences none of this. They cross the boundary normally, watching the universe behind them appear to speed up and grow brighter. Neither perspective is wrong. Both are valid descriptions of the same event, which tells us something profound about the nature of time and space. Our experience of reality is deeply tied to our location and motion through the curved geometry of the universe. Recent theoretical work suggests black holes might not be the information destroyers they appear to be. Some calculations hint that black holes actually radiate energy, slowly evaporating over enormous periods of time. This radiation, predicted by quantum mechanics, carries energy away from the black hole, gradually reducing its mass. For a black hole with the mass of our Sun, this process would take longer than the current age of the universe, multiplied by itself countless times. But here's the fascinating part. This radiation might carry information with it. Not in any obvious way, the radiation appears completely random and thermal, but encoded in subtle correlations between particles. The information that fell into the black hole might slowly leak back out. It would be like burning a book and trying to reconstruct the text from the precise pattern of smoke particles. Theoretically possible, but practically impossible. The edges of our observable universe present similar puzzles about the nature of spacetime. When we look at distant galaxies, we're seeing them as they were billions of years ago, when their light first began its journey toward us, but the universe has been expanding during that entire trip, stretching the wavelengths and making the light redder. There's a boundary out there, beyond which we can never see, not because there's nothing there, but because space itself is expanding so rapidly that light from those regions will never reach us. It's not a wall or barrier, but a horizon created by the fundamental structure of spacetime and the speed of light. This cosmic horizon shares something important with black hole horizons. Both represent limits on information, boundaries beyond which certain knowledge becomes permanently inaccessible. In both cases, the boundary exists not because of physical obstacles, but because of the geometry of spacetime itself. These horizons force us to confront something uncomfortable about our place in the universe. There are questions we can ask that have answers, but answers we can never know. There are regions of reality that remain forever beyond our reach, not due to technological limitations, but because of the fundamental structure of space and time. Perhaps that's the deepest lesson these extreme objects teach us. The universe doesn't owe us complete understanding. There are places where our theories break down, phenomena that exist at the very limits of what can be known. Rather than being frustrating, this might be exactly what we should expect from a universe rich and complex enough to give rise to consciousness in the first place. The mathematics that fails at singularities, the information that seems to vanish, the horizons that hide regions of spacetime from view, these aren't flaws in the universe. They're invitations to think more deeply about the nature of reality itself. Energy and spacetime seem to dance together in ways that stretch far beyond what we can easily picture. The very fabric of space itself expands, and this expansion connects directly to pressure, energy, and the way the universe curves around itself. It's like watching a balloon inflate, except the balloon is everything we know, and the inflation never stops. This expansion creates something almost poetic in its limitations. There are places in the universe that exist, right now, but we will never see them. Not because they're hiding, but because space itself stretches faster than light can travel across it. These regions drift beyond our reach, not through any fault of our telescopes, but through the simple geometry of an expanding cosmos. The universe holds secrets in regions we cannot observe, and this raises questions that keep cosmologists awake at night. Does spacetime behave the same way in those unreachable places? Do the rules we've discovered here, in our tiny visible patch, apply everywhere? We're like people trying to understand an entire ocean by studying a single drop of water. The early universe whispers to us through faint radiation, microwave light that has traveled for billions of years to reach our detectors. This ancient light carries tiny temperature differences, variations so small they require the most sensitive instruments to detect. Yet these whispers tell stories of density fluctuations that eventually grew into galaxies, into stars, into planets, into us. The patterns in this ancient light reveal something extraordinary about spacetime's shape. Some measurements suggest the universe might be perfectly flat, like an infinite sheet of paper. Others hint at subtle curvature, like the surface of a sphere so large we can barely detect the bend. Either way, the uniformity of this radiation poses a puzzle that stretches our understanding. Opposite sides of the sky show nearly identical temperatures in this ancient light, despite those regions never having been in contact during the early universe. It's like finding two people wearing identical outfits who have never met and live on different continents. This observation led scientists to propose cosmic inflation, a period of incredibly rapid expansion that smoothed out the early universe like butter spreading across warm toast. Inflation represents spacetime behaving in ways that seem almost magical. In the tiniest fraction of a second, space stretched so dramatically that quantum fluctuations became the seeds of cosmic structure, its geometry acting dynamically, revealing clues about forces that no longer dominate the universe but once shaped everything we see. The birth of the universe carries hints that spacetime might have been molded by processes completely unlike anything happening today. Those early moments represented a collision between quantum mechanics and relativity, two theories that usually operate in separate domains. Understanding these conditions requires tools we haven't fully developed yet. Theories that bridge scales from the subatomic to the cosmic. The light from those early times has been stretched and dimmed by billions of years of expansion. Each photon carries information, but the message arrives faded and incomplete. Like trying to read a letter that's been left in the rain. We can make out some words, but the full story remains frustratingly elusive. Something even stranger happens when we look at the universe's more recent behavior. The expansion isn't slowing down as we might expect from gravity, pulling everything back together. Instead, it's accelerating, speeding up over time. This acceleration suggests that spacetime itself contains a form of energy we don't understand, something with negative pressure that pushes the universe apart. Dark energy, as scientists call this mysterious component, behaves like a property of empty space itself. It doesn't interact with matter in any obvious way, except through gravity, yet it shapes the geometry of the entire universe. It's as if the vacuum itself contains a hidden spring, constantly pushing outward against the pull of matter. The existence of dark energy tells us that the geometry we observe represents only part of a larger story. If this acceleration continues, the universe might evolve toward a state of profound isolation. Galaxies would drift so far apart that light from one could never reach another, creating new kinds of cosmic boundaries determined purely by the expansion of space. These wouldn't be walls or barriers in any physical sense, but limits imposed by geometry itself. The shape of spacetime would determine what parts of the universe could communicate with each other, and the expansion would gradually increase the cosmic loneliness as structures become more and more isolated. Black holes offer another window into spacetime's stranger properties. Some theories suggest that the event horizon of a black hole might function like a two-dimensional surface that somehow encodes all the information about everything that has fallen inside. It's like having a book's entire contents written on its cover, compressed into a lower dimension, but containing all the same information. This idea extends beyond black holes to encompass the entire universe. Perhaps our three-dimensional reality is itself encoded on some distant two-dimensional surface, like shadows dancing on a wall that represent the full richness of the objects casting them. If true, then studying black hole horizons might reveal fundamental truths about the nature of spacetime itself. When black holes collide and merge, they create ripples in spacetime called gravitational waves. These waves carry information about the extreme curvature that existed during the collision, subtle details that might reveal whether geometry behaves differently than our theories predict in these extreme environments. Each detection adds another piece to a puzzle that spans from quantum mechanics to cosmology. The cosmic boundary that limits our observations isn't fixed like a fence or wall. It moves as spacetime stretches, creating a shifting edge to our observable universe. This boundary offers clues about how geometry evolves over time, how the very fabric of space changes as the universe ages and expands. We can only study a finite region of the universe directly. But this doesn't stop us from making inferences about structures that lie beyond our reach. These inferences depend heavily on our assumptions about how geometry behaves in regions we cannot see. The farther we look, the more we rely on theories that might themselves need updating or replacement. Black holes and cosmic edges point toward places where our current understanding reaches its limits. These are regions where relativity and quantum mechanics collide, where geometry becomes so strange that our mathematical tools strain to describe what might be happening. Yet these extreme environments aren't just curiosities or exotic exceptions to normal physics. They serve as guideposts, showing us where to focus our attention next. They reveal the boundaries of current knowledge and prepare us for discoveries that might completely change our understanding of spacetime itself. The universe seems designed to challenge our assumptions, always keeping new mysteries just beyond our current reach, ensuring that the journey of exploration never truly ends. Physics has this peculiar way of teasing us with mysteries that never fully reveal themselves. There's something almost playful about how the universe operates, showing us just enough to know that something profound is happening, but never quite enough to see the whole picture clearly. Think about how most of science feels relatively straightforward when you get down to it. You can watch a ball roll down a hill. You can see planets moving across the night sky. You can even capture the light from stars that died millions of years ago. These phenomena might be complex underneath, but at least they cooperate with our senses. They give us something to work with. But then there are these other realms of reality that seem almost deliberately secretive. They operate by completely different rules, where the normal methods of observation simply don't apply. It's as if certain parts of the universe have decided that direct scrutiny isn't allowed, that understanding must come through detective work instead of clear observation. Space-time itself embodies this mystery perfectly. Here's this fundamental structure that literally shapes everything we experience, yet it remains completely invisible to us. It's the stage upon which every cosmic drama unfolds, but the stage never steps into the spotlight. Space-time bends light around massive objects. It stretches and compresses under gravitational waves. It even determines how fast time moves in different locations. Yet despite orchestrating all of this, space-time leaves no direct traces of itself. We can only recognize its presence by watching how everything else behaves within it. It's like trying to understand the shape of an invisible container by observing how water moves inside it. The container is absolutely essential to the whole system, but it never announces itself directly. Black holes represent perhaps the ultimate example of this cosmic secrecy. Once anything crosses that event horizon, it disappears from our universe in the most literal sense possible. Not even light, which travels faster than anything else we know, can escape to tell us what's happening inside. If you were floating safely outside a black hole, watching a spacecraft fall toward it, you'd see something truly strange unfold. The spacecraft would appear to slow down as it approached the event horizon. Its light would shift redder and redder until it essentially froze in place and faded from view. But here's the fascinating part. From the perspective of the people inside that spacecraft, nothing unusual happens at all. They cross the event horizon without even noticing it, continuing to fall inward toward whatever lies at the center. Two completely different realities exist simultaneously. One where the spacecraft stops at the horizon forever, another where it passes through and continues its journey. The universe refuses to give us a single, consistent view of what's actually happening. This creates an almost philosophical puzzle about the nature of reality itself. If two observers can witness completely contradictory versions of the same event, which version represents the truth? Perhaps the question itself reveals our limited perspective, our assumption that there must be one correct way to describe what happens. Scientists have developed mathematical models that describe what might exist inside black holes, but these remain purely theoretical. The interior could contain exotic forms of matter, regions where time and space behave in ways we can't imagine, or perhaps something so fundamentally different that our current concepts don't even apply. We simply have no way of knowing. The universe has drawn a curtain that cannot be pulled aside. The early moments of the universe present a similar challenge, but for different reasons. During the first few 100,000 years after the Big Bang, the entire cosmos existed in a state so dense and hot that light couldn't travel freely. Photons would bounce off particles constantly, creating a kind of cosmic fog that blocked any clear view of what was happening. It's as if someone had filled the entire universe with thick clouds, preventing us from seeing the most important events in cosmic history. Eventually, as the universe expanded and cooled, atoms formed for the first time. This cleared the fog, allowing light to travel freely for the first time. That ancient light still reaches us today as the cosmic microwave background, a faint glow that fills the entire sky. But this light can only show us a snapshot of the universe after it had already undergone tremendous changes. The truly crucial early moments, when quantum mechanics and gravity both operated at their full strength, remain completely hidden from direct observation. During that invisible early period, the fundamental forces that govern our universe today might have behaved very differently. Space itself might have expanded faster than light, stretching from quantum scales to astronomical sizes in a fraction of a second. Exotic particles that no longer exist might have filled the cosmos. The very laws of physics might have taken on forms that we can barely imagine today. But all of this remains forever beyond our direct reach, accessible only through mathematical modeling. Dark matter introduces yet another form of cosmic invisibility, one that surrounds us constantly without revealing itself. Galaxies rotate much faster than they should based on the visible matter alone. If ordinary matter were all that existed, most galaxies should have torn themselves apart long ago, flinging their outer stars into intergalactic space. Instead, they hold together as if gripped by some invisible gravitational glue. Galaxy clusters behave similarly, moving as though guided by vast amounts of mass that we simply cannot see. When light from distant objects passes near these clusters, it bends and distorts in ways that reveal the presence of matter that emits no light whatsoever. Every piece of evidence points to the existence of a substance that has mass, that shapes the geometry of space-time, that influences the motion of everything we can observe, yet remains completely invisible to all our instruments. Dark matter doesn't emit light, doesn't absorb light, doesn't reflect. It doesn't seem to collide with ordinary matter in any detectable way. For all practical purposes, it might as well exist in a parallel universe, one that overlaps with ours only through gravitational effects. We know it's there because the things we can see behave as though something invisible is pulling and pushing them. But the dark matter itself remains stubbornly hidden. This creates a somewhat humbling realization about our place in the cosmos. The matter that makes up stars, planets, and our own bodies represents only about 5% of the total mass and energy in the universe. We are literally made of cosmic minority material, while the vast majority of reality consists of substances we cannot directly detect. It's as if we're trying to understand a symphony while being able to hear only a few scattered notes. Dark energy presents an even more puzzling mystery. Observations of distant supernovae revealed that the expansion of the universe is actually accelerating, speeding up over time, rather than slowing down as most scientists had expected. This acceleration requires some form of energy that pushes space itself apart, causing it to stretch faster and faster as time passes. But this dark energy doesn't behave like any form of energy we're familiar with. It doesn't form clumps or structures, it doesn't radiate, it doesn't interact with matter in obvious ways. Instead, it seems to fill all of space uniformly, exerting a constant pressure that drives cosmic expansion. The more the universe expands, the more dark energy appears, as if empty space itself contains an inexhaustible reservoir of this mysterious influence. Scientists can measure the effects of dark energy through careful observations of cosmic expansion rates, but the energy itself remains completely invisible and conceptually elusive. It doesn't fit neatly into any existing theoretical framework. It represents roughly 70% of everything that exists, yet we understand almost nothing about its fundamental nature. It's simultaneously the most important and most mysterious component of our universe. At the smallest scales, quantum mechanics introduces its own form of invisibility through quantum fluctuations. The fabric of spacetime itself appears to be constantly fluctuating at scales far too tiny to observe directly. Particles and antiparticles pop into existence for impossibly brief moments before annihilating each other and disappearing. These quantum fluctuations influence everything around them, but they operate at scales billions of times smaller than atomic nuclei. The evidence for these fluctuations comes through incredibly subtle effects, tiny shifts in energy levels that require enormous precision to detect. Scientists have built instruments sensitive enough to measure these quantum influences, but the fluctuations themselves remain forever hidden behind the limits of what's physically observable. They represent a fundamental graininess to reality itself, a constant background of creative and destructive activity that shapes the universe from the bottom up. Even the curvature of spacetime, which Einstein showed us underlies all gravitational phenomena, never reveals itself directly. When light bends around a massive galaxy, creating those beautiful gravitational lensing effects, we're seeing the consequences of curved spacetime, not the curvature itself. When atomic clocks tick at slightly different rates depending on their altitude, we're witnessing how gravity affects the flow of time, but the underlying geometry remains invisible. It's remarkable how these curved regions of spacetime can be precisely calculated mathematically their effects predicted with extraordinary accuracy. Yet the curvature itself can never be directly observed. We live within this curved geometry constantly. We move through it, we're shaped by it, but we can never step outside to see its overall structure. We're like characters in a painting trying to understand the canvas on which we're drawn. The challenge becomes even more complex when we try to measure gravitational waves, those ripples in spacetime itself that propagate outward from colliding black holes and neutron stars. These waves stretch and compress everything they pass through, including the instruments designed to detect them. The measuring device becomes part of the phenomenon being measured, creating a situation where the signal and the detector are inextricably linked. Facilities like LIGO can detect gravitational waves by measuring changes in distance smaller than 1/10,000th the width of a proton. This represents one of the most precise measurements in the history of science. Yet it still relies on indirect inference rather than direct observation. The waves themselves remain invisible, known only through their effects on carefully calibrated laser beams. Distance creates another form of cosmic invisibility that's perhaps more fundamental than any of the others. The speed of light, despite being incredibly fast by everyday standards, places absolute limits on how far we can see into the universe. Light from the most distant observable galaxies has been traveling toward us for over 13 billion years, showing us what those regions looked like in the distant past, not what they look like today. But the expansion of the universe means that many galaxies that exist today lie beyond our cosmic horizon. Their light will never reach us, no matter how long we wait. These regions might contain phenomena completely unlike anything we observe locally, but they remain forever inaccessible to our instruments and our understanding. The universe could extend infinitely in all directions, filled with wonders we can never discover. This fundamental limitation raises profound questions about the nature of knowledge itself. If vast portions of reality remain permanently hidden from observation, what does it mean to truly understand the universe? Perhaps complete knowledge was never meant to be achieved. Perhaps the mystery and uncertainty are essential features of existence rather than problems to be solved. There's something almost poetic about how the universe reveals itself to us through shadows and echoes, rather than direct illumination. We infer the presence of dark matter through its gravitational influence. We deduce the properties of black hole interiors through mathematical theory. We trace the history of cosmic expansion through the light of ancient supernovae. In each case, reality shows us just enough to know that something remarkable lies hidden, but never enough to satisfy our curiosity completely. This indirect approach to understanding might actually be more profound than direct observation would be. It requires us to develop new ways of thinking, to build conceptual bridges between what we can measure and what we want to understand. It challenges us to remain humble about our knowledge, while still pushing the boundaries of what's possible to discover. Perhaps these invisible aspects of the universe serve a deeper purpose, forcing us to confront the limits of human understanding, while simultaneously inspiring us to develop ever more creative approaches to knowledge. The universe seems to be teaching us that reality is far stranger and more subtle than our everyday experience suggests, that truth often lies hidden behind layers of complexity that require patience and ingenuity to penetrate. In the end, these invisible phenomena remind us that we're still in the early stages of understanding our cosmos. The universe continues to surprise us, to reveal new forms of mystery, just when we think we're beginning to grasp its fundamental nature. And perhaps that's exactly as it should be. A cosmos that challenges us to keep exploring, keep questioning, keep reaching toward truths that always seem to lie just beyond our current grasp. The universe operates like a cosmic magician, constantly pulling its most fascinating secrets just beyond our reach. When we peer into the depths of space, we're not just looking at distant places, we're actually gazing backward through time itself. Every photon that reaches our telescopes carries ancient news, stories from billions of years ago when galaxies were young and the cosmos looked entirely different. This creates a strange patchwork of reality around us. Some galaxies appear as newborns, their first stars just beginning to shine. Others show up in their cosmic middle age, mature and settled. Meanwhile, some might have already collided, merged, or transformed in spectacular ways we'll never witness. The light from those dramatic events simply hasn't had enough time to cross the vast emptiness and reach our instruments. Think about what this means for understanding our place in existence. We're surrounded by a universe where the present moment remains largely invisible to us. The only present we can observe is our immediate neighborhood, while everything else exists for us only as memory frozen in the amber of ancient light. But the cosmic hide-and-seek game goes much deeper than simple distance and time delays. The universe itself is expanding, and this expansion creates its own form of invisibility. Galaxies that we can see today are slowly, inexorably moving away from us. Some will eventually cross an invisible boundary where their light can no longer overcome the stretching of space itself. They'll still exist out there, spinning through the darkness, but they'll fade from our view forever. Future astronomers, working billions of years from now, might look up at a much lonelier sky. Fewer galaxies will twinkle in their instruments. The clues we use today to piece together cosmic history will have vanished, carried away by the relentless expansion of spacetime. In a sense, we're living in a golden age of cosmic observation, able to see a richness that our descendants may never witness. The invisible universe extends down to the smallest scales too, where quantum mechanics rules with an iron fist of uncertainty. Space itself, even what we call empty vacuum, buzzes with constant activity. Virtual particles pop in and out of existence faster than any instrument could ever catch them. These quantum fluctuations happen at scales so tiny and timescales so brief that we can only detect their averaged effects, their statistical shadows. It's like trying to understand a bustling city by only being allowed to see the population statistics. You know something dynamic is happening. You can measure the overall effects, but the individual stories, the moment-to-moment drama of quantum reality, remains forever hidden behind the mathematical veil of uncertainty principles. Even more puzzling, any attempt to peer deeper into these quantum realms hits a fundamental wall. To see smaller structures, you need higher energy probes, but pump enough energy into a small enough region, and gravity itself becomes so strong that it warps or hides the very thing you're trying to examine. The universe seems designed to keep its deepest secrets locked away. This creates profound questions about the nature of knowledge itself. We've built our understanding of reality on observation and measurement, but what happens when the universe systematically prevents us from observing the most fundamental aspects of existence? Perhaps there's a deeper wisdom in this cosmic modesty, a reminder that some mysteries are meant to remain mysterious. The shape of the universe as a whole presents another layer of hiddenness that challenges our cosmic perspective. We can measure the geometry of our observable patch of space-time, and it appears remarkably flat. But this visible region represents only a tiny fraction of what might exist beyond our cosmic horizon. The true universe could curve in ways we haven't imagined, loop back on itself in impossible dimensions, or stretch infinitely in directions we'll never be able to probe. Our cosmic neighborhood might be like a single pixel on a vast cosmic painting, giving us no clue about the overall composition or meaning of the larger artwork. The universe could be finite or infinite, closed like a sphere or open like a saddle, and we might never know which description captures reality. Human perception adds yet another layer of invisibility to our cosmic predicament. Our senses evolved in a world of solid objects and visible light, moderate temperatures, and familiar scales. We never developed intuitive ways to perceive space-time curvature or quantum superposition or the subtle dance of dark energy. Even when our instruments detect these phenomena, we must translate their signals through layers of mathematics before they make any sense to our brains. We're like beings trying to understand a symphony by reading sheet music instead of hearing the music directly. The equations tell us something profound is happening, but the raw experience of curved space-time or quantum uncertainty remains forever beyond our intuitive grasp. Time itself participates in this grand conspiracy of hiddenness. We can observe the past through ancient light, and we can remember our personal histories, but the future remains completely opaque. Will dark energy continue accelerating cosmic expansion forever, or might it change behavior in ways that transform the entire character of reality? Will spacetime itself prove stable over the unimaginable eons ahead? Or might the geometry of existence shift in ways our current theories cannot predict? These questions about cosmic destiny lie hidden behind an impenetrable curtain of possibility. We can make educated guesses based on current observations, but the universe's future behavior remains as mysterious as its deepest quantum foundations. Perhaps there's something almost poetic about this arrangement, this universe that reveals just enough of itself to inspire wonder while keeping its most profound secrets tantalizingly out of reach. We exist in a reality designed, it seems, to keep us humble, to remind us that no matter how sophisticated our instruments become or how elegant our theories grow, mystery will always remain at the heart of existence. The invisible universe surrounds us, not out of malice or cosmic conspiracy, but simply because the same physical laws that allow us to exist also limit what we can know. Light takes time to travel, creating our window into the past. Quantum mechanics restricts how precisely we can measure paired properties. Gravity bends the paths of information and energy. Cosmic expansion carries distant regions beyond our ability to interact with them. We find ourselves in the curious position of being the universe's way of examining itself, but with built-in limitations that ensure the examination can never be complete. Perhaps this incompleteness is not a flaw in our cosmic situation, but rather an essential feature. The thing that keeps existence interesting and maintains the sense of wonder that drives us to keep looking up at the stars. All across the cosmos, there are things we simply cannot see. Black holes hide their interiors from us completely. The early universe remains locked away behind barriers of time and distance. Vast regions of space sit so far beyond our reach that their light will never arrive. Dark matter fills the universe, but refuses to interact with anything we can detect directly. These invisible territories create a strange situation. Most of what exists stays hidden from our instruments and our eyes. We build theories to fill in the gaps, but we're always working with incomplete information. Relativity describes how massive objects bend space on large scales. Quantum mechanics explains the behavior of particles at tiny scales. Cosmology tries to piece together the story of how everything began. Each field of physics tackles its own piece of the puzzle, but they all rely on indirect clues rather than direct observation. It's like trying to understand a house by examining only the shadows it casts at different times of day. You can learn quite a lot from shadows, but you're always making educated guesses about what's creating them. Temperature feels real when you touch something hot or cold, but temperature isn't actually a fundamental part of reality. It emerges from the motion of countless tiny particles bouncing around. Pressure pushes against your skin when you dive underwater, but pressure is just the combined effect of water molecules bumping into you. Even color, which seems so basic and obvious, comes from interactions between light waves and the biological machinery in your eyes. These examples share something important. They're all real phenomena that we experience directly, but they're not building blocks of the universe. They're behaviors that emerge when simpler components interact in large numbers. The motion of particles creates temperature. The collisions of molecules create pressure. The interaction of light and biology creates color. This raises a fascinating question about space and time themselves. We tend to think of space-time as the stage where everything else happens. It feels fundamental, like it should exist whether anyone is around to observe it or not. Gravity works by bending space-time. Light travels through it. Matter moves within it. But what if space-time itself is more like temperature or pressure? What if it's real and useful, but not actually fundamental? Some physicists have started wondering whether space-time might be emergent too. Not fake or imaginary, but secondary to something deeper. This idea comes partly from the difficulties we face when trying to combine relativity with quantum mechanics. Both theories work beautifully on their own, but they treat spacetime in completely different ways. Relativity allows spacetime to bend and stretch like a flexible fabric. Massive objects create curves in this fabric, and those curves guide the motion of everything else. Quantum mechanics, though, relies on fixed backgrounds. It doesn't expect time and space to bend or change shape. When you try to merge these approaches, They contradict each other at the deepest level. This mismatch hints that maybe space-time isn't the common foundation we thought it was. Maybe it's more like a useful approximation that works well under certain conditions, but breaks down when we look too closely. Quantum entanglement adds another layer to this puzzle. When particles become entangled, they remain connected in ways that don't seem to care about distance at all. You can separate entangled particles by light years, and they'll still coordinate their behavior instantly. This connection doesn't weaken as the particles move apart. It doesn't seem to travel through space-time the way other interactions do. It operates according to rules that seem independent of geometry altogether. Some researchers have suggested that entanglement might be more fundamental than the structure of space and time. In this view, the relationships between quantum states could give rise to space-time rather than existing within it. The geometry we observe could be a product of deeper quantum connections, not the arena where those connections play out. This perspective got more attention when mathematicians discovered something unexpected about black holes. The amount of information that a black hole can contain seems to depend on its surface area, not its volume. In ordinary experience, the information capacity of something depends on the space inside it. A larger box can hold more books than a smaller one, but black holes appear to work differently. Their information storage relates to their surface area instead. This suggests that what we think of as three-dimensional space might actually be a projection of information stored on a two-dimensional boundary. Not an illusion exactly, but an emergent structure that arises from something with fewer dimensions. Scientists sometimes call this the holographic principle. Though it's not about holograms in the science fiction sense, it's the idea that space-time and everything within it might emerge from deeper information encoded in a completely different kind of structure. In this picture, space-time wouldn't be the foundation of reality. It would be a higher-level description that emerges from something more abstract but more fundamental. Gravity itself provides another reason to question whether space-time is basic. According to relativity, gravity isn't really a force like electromagnetism. It's the curvature of space-time itself. Massive objects don't pull on other objects directly. They bend the geometry of space and time, and other objects follow the curves created by that bending. But if space-time is emergent, then gravity would be emergent too. Some scientists have explored whether gravitational effects could arise from statistical processes, similar to how temperature emerges from molecular motion. In these models, the smooth curves of spacetime would represent the average behavior of some deeper, more chaotic system. The geometry we observe would be like the surface of a calm lake. From a distance, the surface looks smooth and continuous, but if you could zoom in far enough, you'd see that it's actually made of countless water molecules bouncing around individually. The smoothness only appears when you average over huge numbers of particles. If spacetime works this way, then at very small scales, the smooth geometry would dissolve into something more granular or more abstract. The flowing curves that guide planets around stars and bend light near massive objects would be emergent properties of underlying interactions we haven't identified yet. These ideas remain theoretical rather than confirmed science. But the mathematics works in certain models, and that suggests our usual picture of spacetime might be incomplete. We might be looking at reality from only one level, missing the deeper structures that give rise to the space and time we experience. This possibility changes how we think about our place in the universe. We're used to seeing ourselves as observers studying an external reality. We measure distances, track the passage of time, and map the geometry of space. But if spacetime is emergent, then the framework we use to make those measurements might be shaped by the limitations of our perspective. The universe we observe could be real and accurate within its own context, but still be just one layer of a much deeper structure. Like temperature, or pressure, or color, spacetime could be completely genuine, while still being secondary to something more fundamental. The question isn't whether space and time exist, but whether they're the most basic level of description, or whether they arise from interactions we haven't learned to detect yet. When you try to measure incredibly tiny distances, the universe seems to push back against your efforts. It's as if reality itself has a minimum resolution, like pixels on a screen. that can't be divided any further. Below a certain scale, the very idea of distance starts to lose its meaning. The measuring tools break down, the mathematics becomes chaotic, and what once seemed solid begins to dissolve. This resistance might tell us something profound about the nature of existence itself. Our brains developed to navigate a world of clear boundaries, obvious directions, and steady time. We needed to distinguish between here and there, between before and after. These concepts feel so natural that we assume they must be woven into the fabric of reality. But perhaps they're more like shadows cast by something deeper, something our minds can't directly grasp. Throughout history, what seemed fundamental often turned out to be an illusion. Ancient philosophers thought atoms were the smallest possible pieces of matter. The word itself means indivisible. Then scientists discovered that atoms contain protons, neutrons, and electrons. Later, they found that protons and neutrons are made of even smaller particles called quarks. Each time we looked closer, the supposedly solid foundation crumbled into smaller components. Space might follow this same pattern. What appears smooth and continuous at our scale could break apart into discrete pieces when examined closely enough. Those pieces might not look like geometry at all. They could be abstract mathematical structures, networks of pure information, or patterns of connection that have no resemblance to the space we experience. Think about how different theories treat time in completely different ways. In Einstein's relativity, time bends and stretches along with space. Gravity can slow it down, motion can speed it up. Time becomes part of a unified fabric called spacetime. But in quantum mechanics, time behaves like a simple clock ticking away in the background. It doesn't bend, it doesn't stretch, it just moves forward at a steady pace. If spacetime were truly fundamental, you'd expect all theories to treat time the same way, but they don't. This disagreement suggests that time, and therefore spacetime, might be something that emerges only under certain conditions, like how wetness emerges when you have enough water molecules together, but individual molecules aren't wet by themselves. The expansion of the universe adds another layer to this puzzle. Astronomers tell us that space itself is stretching, carrying galaxies away from each other. But what exactly is doing the stretching? If space were fundamental, this might make immediate sense, that if space emerges from something else, then the expansion becomes the behavior of a deeper system following rules we don't yet understand. Dark energy, that mysterious force accelerating the expansion, might not be a property of space at all. It could be a sign that space is just one layer of a much more complex structure. Like ripples on a pond, the ripples aren't really about water, they're about energy moving through water. The expansion might be energy moving through whatever creates the illusion of space. Many of the most ambitious theories in physics start without space-time and try to build it from scratch. String theory begins with tiny vibrating strings whose interactions somehow generate the space and time we experience. Other approaches start with networks of abstract connections, or pure information, or causal relationships between events. In each case, space-time appears later in the story, not at the beginning. This is like discovering that what you thought was a painting is actually a tapestry. From far away, it looks like a smooth surface with colors and shapes. But up close, you see individual threads woven together in complex patterns. The painting is still there, still beautiful, still meaningful. But it's not what you thought it was. It's something that emerges when simpler elements combine in the right way. Water provides a useful analogy here. When you look at a lake, you see a smooth surface. You can describe its behavior with equations about fluid flow and surface tension. Those equations work perfectly for most purposes, but water is actually made of individual molecules bouncing around chaotically. The smooth surface is real, but it's not fundamental. It's what happens when billions of molecules interact according to much simpler rules. Space-time might work the same way. It could be the smooth surface that emerges when countless tiny discrete elements interact according to rules that have nothing to do with geometry. The elements themselves might not have location or duration, They might not move through space because there wouldn't be any space for them to move through. Space would be something they create collectively, like a crowd of people, creating the shape of a stadium by standing in the right places. This idea helps explain why relativity and quantum mechanics seem to contradict each other. Relativity excels at describing the smooth, emergent surface when you're dealing with large scales. Quantum mechanics excels at describing the underlying discrete elements when you're dealing with small scales. But when you try to use relativity at quantum scales, you're essentially trying to describe individual molecules using equations meant for smooth water surfaces. And when you try to use quantum mechanics at large scales, you're trying to track individual molecules when all you care about is the overall flow of the river. The mathematical infinities that plague attempts to combine these theories might be artifacts of using the wrong model at the wrong scale. It's like trying to count the pixels in a photograph by measuring the brightness of the overall image. The tools don't match the task, so you get nonsensical answers. If space-time is emergent, then many of the deepest mysteries in physics take on new meaning. Black holes, where space-time curves so extremely that it breaks, might be regions where the underlying structure behaves in ways that can't be translated into the language of smooth geometry. The Big Bang, when space-time itself supposedly began, might be the moment when the deeper structure first organized itself in a way that creates the illusion of space and time. Even the strange behavior of quantum particles starts to make more sense. When particles seem to be in multiple places at once, or when they influence each other instantly, across vast distances, maybe they're not actually moving through space at all. Maybe they're different aspects of the same underlying pattern, like different pixels on a screen, that appear separate but are actually controlled by the same computer program. This perspective transforms our understanding of motion, distance, and duration. Instead of being fundamental features of reality, they become useful approximations that work well at the scale of human experience. They're like the apparent motion of the sun across the sky, which is real and observable and useful for navigation, but doesn't reflect what's actually happening in the solar system. The philosophical implications stretch far beyond physics. If the most basic features of our experienced reality are emergent rather than fundamental, what does that say about the nature of existence itself? We live in a universe that appears to be built from the bottom up, but might actually be organized from some deeper level that we can barely imagine. This doesn't diminish the reality of our experience. Lakes are still wet, even though they're made of molecules. Time still flows, even if it emerges from something timeless. Space still extends in all directions, even if it's woven from elements that have no location. But it suggests that reality has depths we haven't begun to explore, layers beneath layers stretching down towards some ultimate foundation that might be stranger and more beautiful than anything we've yet conceived. When scientists push their best theories to the very edge, something fascinating happens. The elegant equations that explain so much of our world suddenly start to wobble. Numbers refuse to cooperate. Predictions become fuzzy. It's like standing at the shore of an ocean, knowing there's something profound beyond the waves, but never quite being able to wade in completely. This moment of almost knowing, almost grasping the complete picture, defines much of modern physics. We have theories that work beautifully, explaining vast chunks of reality with stunning precision. They guide spacecraft to distant planets, power our technology, help us understand stars and atoms alike. Yet when we stretch them just a little further, toward the deepest questions about space and time, they begin to crack. Consider the two pillars of modern physics. General relativity paints gravity as the curvature of space-time itself. Massive objects bend the fabric of reality, creating what we experience as gravitational pull. This theory predicted black holes decades before we found them. It explains why time runs slower in strong gravitational fields. It describes how the universe expands, how light bends around massive objects, how GPS satellites need constant adjustments to account for time dilation. On the other side sits quantum mechanics, perhaps the most precisely tested theory in all of science. It reveals a universe where particles exist in multiple states simultaneously, where the act of observation changes reality, where uncertainty isn't just a limitation of our instruments, but a fundamental feature of nature itself. Every computer chip, every laser, every medical imaging device relies on quantum principles. Both theories work magnificently within their domains. But when physicists try to combine them, especially in extreme situations like the center of black holes or the first moments after the Big Bang, the mathematics breaks down. The equations produce infinite answers, which in physics usually means you've pushed your theory past its breaking point. There's something almost poetic about this limitation. Here we are, conscious beings made of quantum particles, living in curved spacetime, yet unable to fully describe the marriage between these two aspects of reality. It's as if nature guards its deepest secrets behind a veil that our current understanding can only partially lift. The search for unity has taken many forms. Grand unification theories suggested that at extremely high energies, the forces we see as separate, electromagnetism, the strong nuclear force, the weak nuclear force, were once aspects of a single interaction. In the furnace of the early universe, these distinctions vanished. Only as the cosmos cooled did the forces split apart, like different colors emerging from white light passed through a prism. This idea carries a certain elegance. Maybe the complexity we observe, the seemingly random collection of particles and forces, actually reflects fragments of a simpler, more unified past. But even grand unification leaves gravity out of the picture, standing apart like a puzzle piece from a different box. The standard model of particle physics represents another triumph that falls just short of completeness. This framework organizes all known particles into neat families, explains their interactions, predicted particles before experiments found them. It's been tested in countless ways and passed every examination. Yet explains perhaps 5% of the universe. The rest, dark matter and dark energy, remain mysterious. The model works perfectly for what it describes, but leaves the vast majority of cosmic reality unexplored. Scientists have wondered whether extra dimensions might hold the key. Perhaps our familiar 3 dimensions of space and one of time represent only a slice of a larger reality. Gravity might seem weak compared to other forces, because some of its influence leaks into these hidden dimensions, like sound escaping through cracks in a wall. The mathematics of extra dimensions can be beautiful, offering elegant solutions to various puzzles. But here's where science meets the humbling nature of reality. Despite decades of searching, no experiment has revealed these extra dimensions. They remain mathematical possibilities rather than confirmed features of our universe. It's a reminder that nature doesn't always conform to our most elegant theories, no matter how mathematically appealing they might be. String theory emerged as perhaps the most ambitious attempt to weave everything together. Instead of imagining particles as tiny points, string theory pictures them as minuscule vibrating loops. Different vibration patterns correspond to different particles, like different notes played on cosmic instruments too small to imagine. In this framework, gravity naturally emerges as one of the possible vibration modes. For the first time, physicists had a theory that seemed to incorporate both quantum mechanics and gravity, without producing those troublesome infinite answers. The theory sparked enormous excitement, because it promised to unify not just gravity and quantum mechanics, but all the forces and particles in a single mathematical framework. Yet string theory brings its own challenges. It requires extra dimensions, specific symmetries, mathematical structures that remain undetected. The strings themselves vibrate at scales so tiny that directly observing them may be impossible with any conceivable technology. The theory remains beautiful, promising, and largely untestable. This situation reveals something profound about the human quest for knowledge. We've built theories that explain an extraordinary range of phenomena, from the behavior of atoms to the evolution of galaxies. We can predict eclipses centuries in advance, design molecules with specific properties, peer back toward the birth of the universe itself. Yet the deepest unity, the theory that would seamlessly connect quantum mechanics with gravity, remains elusive. Perhaps this limitation reflects something fundamental about the nature of knowledge itself. Maybe complete understanding always stays just beyond our grasp. no matter how far we extend our intellectual reach. Or maybe we're simply still climbing toward a summit we haven't yet glimpsed, gathering pieces of a puzzle whose final picture remains hidden. The persistence of these boundaries, these places where our best theories strain and crack, might actually be essential to the scientific enterprise. They remind us that reality exceeds our current understanding, that there are always new questions to explore, new mysteries to unravel. In a strange way, the incompleteness of our knowledge keeps the universe interesting. Modern physics finds itself in a curious position where theories come tantalizingly close to explaining everything, yet always seem to fall just short of the complete picture. Scientists have developed ideas that suggest space-time itself might not be the fundamental reality we once thought it was, but something that emerges from deeper, more basic components. Some researchers propose that what we experience as space-time actually arises from objects called brains, which exist in higher dimensions than the three spatial dimensions we're familiar with. Think of it like shadows on a wall, where our entire universe might be just a shadow cast by something far more complex existing in dimensions we can't directly perceive. The mathematics behind these ideas suggests that our universe could literally be the boundary, the edge, of a much larger, higher dimensional space. Other approaches take a completely different direction, suggesting that space-time emerges from networks of quantum states, like a fabric woven from the strange connections between particles at the smallest scales. These quantum relationships somehow give rise to the smooth, continuous space and time that we experience in our everyday lives. The beauty of these ideas lies in how they might finally bridge the gap between quantum mechanics, which governs the very small, and relativity, which describes gravity and the very large. Yet despite their mathematical elegance, these theories remain stubbornly theoretical. They explain many things, but never quite everything, always leaving some crucial questions unanswered. Another fascinating approach suggests that space-time isn't smooth at all, but has a discrete structure when you look closely enough. Imagine zooming into what appears to be a smooth photograph until you can see the individual pixels. Some theories propose that space-time is made up of tiny loops, woven together into an intricate network. At large scales, this network appears perfectly smooth, just like a photograph viewed from a distance. But at the smallest possible scales, the granular, pixelated structure becomes apparent. This loop-based approach solves some major problems that plague other theories. When physicists try to calculate certain properties of gravity at quantum scales, they often get infinite answers, which clearly can't be right. The discrete structure of these loop theories naturally avoids those troublesome infinities, providing finite answers that make mathematical sense. However, testing these ideas experimentally remains incredibly challenging, and the theories haven't yet succeeded in unifying gravity with the other fundamental forces. Some scientists have taken an even more radical approach, treating space-time not as something that exists independently, but as something that emerges from the relationships between events. In this view, space-time doesn't exist until something actually happens. The connections between these events, the ways they influence each other, create the geometry of space and time itself. This removes the need to think of space-time as a fixed background stage where physics plays out, which helps avoid some of the contradictions that arise when quantum mechanics meets gravity. But transforming these causal relationships into the smooth geometry we observe requires making many assumptions, and connecting these ideas to experiments that could test them remains difficult. Perhaps even more intriguing are the theories that approach the problem from the perspective of information itself. Instead of treating space-time as a physical object, these ideas suggest it emerges from how information gets stored and shared among quantum systems. In this picture, the strange quantum phenomenon of entanglement doesn't just connect particles across vast distances, it actually shapes the geometry of space-time itself. Distances between points in space might emerge from how strongly quantum states are linked together. The curvature of space-time, which we experience as gravity, might arise from the patterns of how information flows between quantum systems. These ideas create compelling mathematical connections between several puzzling features of black holes and quantum fields, but they're still in their infancy. They haven't yet been developed into complete, testable theories that can explain all the physics we observe. Even inflation theory, which successfully explains many features of the early universe, has significant gaps. Inflation describes how the universe expanded rapidly in the first tiny fraction of a second after the Big Bang, smoothing out irregularities and producing the remarkable uniformity we observe in the cosmic microwave background radiation. The theory predicts many of the patterns we see in this ancient light, and it explains why space appears to be nearly flat on the largest scales. But inflation requires very specific conditions to get started, and the theory doesn't explain where those initial conditions came from. Moreover, inflation predicts not just one possible universe, but a whole variety of different universes depending on the precise details of how it unfolds. This raises profound questions about whether inflation describes fundamental physics or just represents one version of a much broader set of possibilities. Quantum field theory, the incredibly successful framework underlying the standard model of particle physics, also encounters limits when pushed to extremes. This theory describes particles and forces as excitations, like waves, in fields that spread throughout spacetime. It works extraordinarily well under normal circumstances, but when applied in curved spacetime, especially near black holes or during the rapid expansion of the early universe, new puzzles emerge. The theory predicts that what we call empty vacuum isn't actually empty at all, but filled with quantum fluctuations, tiny temporary disturbances in the quantum fields. But when physicists calculate how much energy these fluctuations should contribute, they get an answer that's far too large. If this prediction were accurate, spacetime would curve so violently that the universe would look nothing like what we observe. Yet clearly, this doesn't happen. Something about the relationship between vacuum energy and gravity simply refuses to work out properly. Supersymmetry offered another elegant possible extension to our understanding. This theory suggests that every known particle has a heavier counterpart, a supersymmetric partner. If supersymmetric were real, it could solve several major problems simultaneously. It could explain the mysterious dark matter that makes up most of the universe's mass. It could stabilize the quantum vacuum. It could unify the fundamental forces at high energies, bringing us closer to a theory of everything. Despite decades of intensive searching, however, no supersymmetric particles have been discovered. The idea remains mathematically beautiful and theoretically compelling, but nature has so far declined to reveal any evidence for it. Dark matter itself presents an ongoing puzzle that illustrates how close, yet how far, our theories can be. Some approaches propose that dark matter consists of undiscovered particles that interact only weakly with ordinary matter. Other theories suggest that gravity itself behaves differently on the largest scales, eliminating the need for dark matter entirely. These modified gravity theories can produce interesting results, especially when applied to specific systems like individual galaxies, but they struggle to explain all the diverse evidence for dark matter consistently across different scales and situations. Like so many other approaches, they almost explain everything, but not quite. Even the grand goal of unifying all fundamental forces into a single theoretical framework encounters stubborn obstacles. Each attempt requires conditions that may not exist in reality, or relies on energy so high that we cannot access them experimentally. When these theories venture into regimes where quantum mechanics and gravity collide head-on, the mathematics becomes extraordinarily complex and often predicts particles we haven't found or behaviors that conflict with careful observations. The beauty of these theories often derives more from their mathematical consistency than from their empirical success, which raises deep questions about the relationship between mathematical elegance and physical truth. These near misses in theoretical physics reveal something profound about the nature of scientific understanding. The universe isn't withholding some final answer out of stubbornness. Rather, these theories are showing us exactly where their strengths and limitations lie. Each approach captures an important part of the overall picture, but none captures everything. This suggests that the ultimate truth might require combining ideas from multiple approaches rather than finding one single tidy solution. Alternatively, the next major breakthrough might require a completely new perspective, something that fundamentally reframes our understanding of space-time and its relationship to matter, energy, and information. Such paradigm shifts have happened before, in physics, completely changing how we think about reality itself. Despite their limitations, these almost successful theories serve a crucial role in guiding scientists toward the point where the missing pieces might finally appear. They reveal patterns that repeat across different models, showing which features seem to be essential aspects of nature and which might be mere artifacts of the mathematical methods being used. These theories teach researchers where contradictions inevitably arise and where long-held assumptions begin to break down. In this sense, even the failures are successes, each one mapping out another region of the vast landscape of possible explanations for how reality works at its most fundamental level. Looking ahead into the future of physics feels a bit like wandering through an endless maze, where every turn reveals something unexpected. The deeper we dig into the nature of reality, the more we realize that our most cherished assumptions might be completely wrong. It's a humbling thought, really, that despite all our sophisticated instruments and elegant equations, we're still just scratching the surface of how the universe actually works. The history of physics teaches us one thing very clearly: nothing unfolds the way we expect it to. When Einstein came along with relativity, nobody saw it coming. Space and time weren't supposed to be flexible, stretchy things that could bend and warp. They were supposed to be fixed, unchanging backdrops for everything else. But suddenly, here was this wild idea that massive objects could literally curve the fabric of reality itself. It changed everything we thought we knew about how the cosmos operates. Quantum mechanics did something even stranger. It took the nice, predictable world of classical physics and turned it into a probabilistic wonderland where particles exist in multiple states at once, where the act of observation changes what you're looking at, where things can be connected across vast distances in ways that seem to defy common sense. These aren't just abstract mathematical curiosities, they're fundamental features of how nature behaves at its most basic level. Then cosmology dropped another bombshell. The universe isn't static, it's expanding, stretching itself larger every second. This revelation came from looking at distant galaxies and noticing that they're all moving away from us, and the farther away they are, the faster they're receding. It's as if space itself is growing, carrying everything along for the ride. This discovery fundamentally changed how we think about the past, present, and future of everything that exists. Dark matter added another layer of mystery. We can see its gravitational effects, the way it bends light from distant objects, how it shapes the rotation of galaxies, but we can't directly detect it. Something invisible, something that doesn't interact with light or ordinary matter in obvious ways, makes up most of the mass in the universe. It's like discovering that most of reality is hidden from our senses, operating behind the scenes in ways we're only beginning to understand. Dark energy is even more puzzling. This mysterious force appears to be pushing the expansion of the universe to accelerate, working against gravity on the largest scales. It makes up about 70% of everything that exists, yet we have no real idea what it is or how it works. The very fabric of space-time seems to be infused with this strange energy that wants to make everything spread apart faster and faster. Each of these discoveries came as a shock because they didn't fit into the existing framework. They forced scientists to completely rethink their basic assumptions about reality. This pattern suggests that whatever comes next will probably be equally surprising, equally challenging to our current understanding. Right now, physics faces several major puzzles that refuse to fit together nicely. Quantum mechanics and gravity don't play well together. At the smallest scales, quantum effects should dominate, but we don't really know how gravity behaves in that realm. This creates problems when trying to understand what happens inside black holes, what occurred during the first moments after the Big Bang, or what spacetime itself is made of at its most fundamental level. The nature of dark matter remains completely mysterious. We know it's there, we can measure its effects, but identifying what it actually is has proven incredibly difficult. It could be some exotic type of particle that rarely interacts with ordinary matter. It could be something stranger, like modifications to how gravity works on large scales, or signs that spacetime itself has properties we haven't discovered yet. dark energy presents an even deeper mystery. If it's truly a property of space itself, then empty space isn't really empty, it's filled with this invisible energy that drives cosmic expansion. But the amount of dark energy we observe is wildly different from what our best theories predict. This suggests we're missing something fundamental about how the universe works at its largest scales. Black holes create their own set of puzzles. What happens to information that falls into them? How does the interior connect to the exterior? What goes on at the event horizon where time and space become so warped that our usual descriptions break down? These aren't just academic questions, they point to gaps in our understanding of how space-time, matter, and information relate to each other. One approach to solving these puzzles involves trying to unify all the fundamental forces into a single, coherent framework. The idea is appealing, almost elegant in its simplicity. If everything emerges from one underlying principle, then all these apparent contradictions might resolve themselves naturally. Gravity, electromagnetism, and the nuclear forces would all be different aspects of the same phenomenon, just as electricity and magnetism turned out to be two sides of the same coin. But unification has proven incredibly difficult. Each attempt to merge quantum mechanics with gravity introduces new mathematical complexities, new abstract concepts that become harder and harder to connect with actual observations. String theory, loop quantum gravity, and other approaches have made progress, but they've also revealed just how deep and challenging these problems really are. Another fascinating possibility involves thinking about the universe in terms of information rather than matter and energy. In this view, everything that exists, including space-time itself, emerges from underlying informational processes. Particles, fields, and forces would all be different ways that information gets organized and processed. The geometry of space and time would reflect how information flows and gets entangled across different regions. This informational approach could help explain why quantum entanglement plays such a central role in physics. When particles become entangled, they share information in ways that seem to transcend ordinary spatial separation. If information is truly fundamental, then entanglement might be the basic mechanism by which reality holds itself together. Space-time might be more like a network of relationships than a physical container. The nature of time itself might need to be reconsidered. Right now, different areas of physics treat time very differently. Relativity weaves time together with space into a unified space-time that can curve and stretch. Quantum mechanics treats time as an external parameter that ticks forward at a steady rate. This mismatch hints that we don't really understand what time actually is at the deepest level. Perhaps time isn't fundamental at all. At one isn't fundamental at all. Maybe it's something that emerges from more basic processes, like temperature emerges from the motion of molecules, or pressure emerges from countless molecular collisions. If time is emergent, then the familiar experience of flowing from past to future might be similar to how wetness emerges from water molecules, a higher level property that doesn't exist at the most basic level. There's also the intriguing possibility that we haven't discovered all the basic ingredients of reality yet. When we talk about dark matter, we often assume it will turn out to be some type of particle, but it could be something completely different. It might be a new kind of field that permeates space, or a sign that the structure of space-time itself changes behavior on very large scales. Dark energy might not be energy in any conventional sense. It could be evidence of some larger process that shapes the geometry of the universe over cosmic timescales. Perhaps it's related to how space-time itself evolves, grows, or changes its properties as the universe ages and cools. The smaller scales of reality remain almost completely mysterious. We can't directly observe what happens when distances shrink down to the Planck scale, where quantum effects on space-time itself should become important. At those incredibly tiny scales, the familiar picture of smooth, continuous space and time might break down entirely. Distance and duration might become fuzzy, approximate concepts that only make sense when you zoom out to larger scales. If space-time is actually discrete rather than continuous at the smallest scales, like a digital image is made of individual pixels, then many of the contradictions between quantum mechanics and relativity might resolve themselves naturally. The apparent incompatibility might come from trying to describe smooth geometry in a realm where smoothness doesn't exist. These various possibilities paint a picture of physics standing at a crossroads. The questions we're asking are becoming deeper and stranger. We're not just trying to catalogue new particles or measure constants more precisely. We're questioning the very foundations of space, time, matter, and information. We're wondering whether our basic categories for understanding reality are adequate, or whether they need to be completely reimagined. The philosophical implications are profound. If time is emergent, what does that say about memory, causation, and free will? If space-time arises from information, what does that mean for our sense of existing in a physical universe? If unification is possible, does that suggest an underlying unity to all existence? If multiple universes exist, how does that change our understanding of what it means for something to be real? These aren't just abstract puzzles for theoretical physicists to ponder. They touch on some of the deepest questions humans have always asked about the nature of existence, the structure of reality, and our place within the cosmic order. The answers, when they come, will likely be as surprising and transformative as anything we've discovered before. Mathematics holds secrets that haven't found their way into physics yet. Throughout history, mathematical concepts that seemed completely abstract eventually became the language for describing reality. Non-Euclidean geometry existed purely in the minds of mathematicians, until Einstein showed us that space-time itself curves. Complex numbers were just mathematical curiosities, until quantum mechanics revealed they're essential for describing wave functions. Group theory seemed like an esoteric branch of mathematics, until physicists realized it perfectly organizes the symmetries that govern fundamental particles. Today, entire mathematical frameworks sit waiting, with no apparent connection to the physical world. These mathematical structures might hold the keys to understanding phenomena we can't even imagine yet. The intersection of pure mathematics with physical reality often produces the most profound breakthroughs. Perhaps the behavior of spacetime, the dance of quantum fields, and the evolution of the cosmos will eventually look like natural consequences of some deeper mathematical truth we haven't discovered yet. But mathematics alone might not be enough. The next great leap in physics might require us to abandon our most basic assumptions about how to think about the universe. Humans are spatial creatures. We think in terms of objects moving through space. We rely on visual metaphors. We imagine relationships between things we can picture in our minds. This works well for everyday experience, but reality at the smallest scales and at the largest scales might not conform to these intuitive ways of thinking. Future physics might demand that we learn to think in completely unfamiliar ways. Instead of imagining space as a container for objects, we might need to think of reality as a network of relationships. Instead of focusing on things, we might need to focus on processes. Instead of treating fields as substances that fill space, we might discover their manifestations of deeper layers of reality that don't resemble anything we currently call physical. Even causality, something so fundamental to our experience that we rarely question it, might need to be reconsidered. In everyday life, causes led to effects in clear, orderly chains, but quantum mechanics has already started to challenge this simple picture. Some quantum processes seem to happen without a clear causal order. Entangled particles behave as if they're sharing information outside the normal rules of cause and effect. Some theoretical frameworks suggest that causality itself might not be a fundamental feature of reality. Instead, it might be something that emerges, something that appears only under certain conditions, like the way temperature emerges from the motion of molecules. If causality turns out to be an emergent property, rather than a basic rule, it would transform how we model everything from particle interactions to cosmic evolution. Observational technology will play a crucial role in shaping whatever comes next. New telescopes are being designed to peer deeper into space and further back in time. Gravitational wave detectors are becoming more sensitive, potentially allowing us to hear echoes from the earliest moments of the universe. Particle accelerators might discover new particles that don't fit current theories, or they might rule out entire classes of theoretical models. Space-based instruments could detect subtle changes in the expansion of space itself, or reveal patterns in gravitational fields that point toward completely new physics. Each new measurement becomes a clue, a piece of evidence that either supports existing theories or suggests they need to be replaced. However, the universe imposes fundamental limits on what we can observe. We can only see as far as light has had time to travel. We can only measure things as precisely as quantum uncertainty allows. We can only study phenomena that produce detectable effects. Vast portions of reality might remain forever beyond our reach. But even these limitations can guide theoretical development. They tell us where the gaps in our knowledge lie, where our models break down, and what kinds of explanations might work across those boundary regions where observation fails us. The future of physics might require accepting that some questions don't have single, clean answers. The universe might not be built from one unified structure, but from layers, each with its own rules, each emerging from the layer beneath it. Spacetime might emerge from quantum processes. Quantum processes might emerge from symmetries. Symmetries might arise from even deeper patterns that don't resemble anything we would recognize as physical. This layered view could lead to a more flexible understanding of reality, where the focus shifts to understanding how each level connects to the next, rather than searching for one theory that explains everything at once. The connections between layers might be just as important as the layers themselves. Many ideas that seem fringe or speculative today might become mainstream tomorrow. Quantum mechanics was once considered too strange to be true. Relativity was dismissed as overly radical. The expansion of the universe was met with skepticism. Revolutionary ideas often begin at the margins, seeming impossible until they become inevitable. Theories that appear unconventional now might simply be in their early stages of development. Their current limitations might not reflect fundamental flaws, but rather the growing pains that come with any genuinely new way of understanding reality. Just as likely is the possibility that the next breakthrough is hiding in plain sight, disguised as something too simple or too obvious to notice. Many advances in physics came from paying attention to small details that didn't seem important at first. A tiny anomaly in Mercury's orbit led to general relativity. The ultraviolet catastrophe led to quantum mechanics. The faint, uniform glow of the cosmic microwave background revolutionized cosmology. The future might depend on someone noticing an equally subtle clue, something that's been staring at us all along but doesn't fit the patterns we expect based on current theories. Sometimes the most profound discoveries come not from building bigger machines or developing more complex mathematics, but from asking simpler questions about things we thought we already understood. There's something deeply moving about being part of this ongoing process of discovery. Every scientist contributes a small piece, every measurement adds a fragment, every idea, even the ones that turn out to be wrong, nudges our collective understanding forward. The future of physics isn't a race to reach some final answer, but an ongoing collaboration between human curiosity and the universe itself. We observe, we ask questions, we test ideas, we adjust our theories, and slowly, piece by piece, we reveal more of what lies beneath the surface of everyday experience. As these questions keep expanding, as theories keep reaching toward deeper possibilities, the path ahead remains open, inviting continued exploration into the fundamental nature of everything we know and everything we have yet to discover.